Hi everyone, welcome to Vedantu NEET English. I'm Diksha Kaushal, your chemistry master teacher. And guys, how are you all? Very good evening to everyone here. Very good evening. So guys, we have almost completed our syllabus, right? We are just left with one chapter, that is P block, and another we are left with this practical chemistry, right? Practical chemistry with go, like I will do that after some time because that is something, most of the things are related to what you have done in physical, organic and inorganic chemistry, right? So the difference, the part that is not, that you have not studied is salt analysis, right? So I will make a separate lecture on salt analysis. Rest of the topics we will do it in a marathon itself. Okay, yes everybody, very good evening, very good evening. So today we are going to do which thing? P block, right? As you can see the topic, as you can see the title, it's P block, group number 13 and 14. So many students are confused in this, that ma'am, whether it's in our syllabus or not. So guys, see, as you know that officially the syllabus, but you know, when you talk about group P block, even last year, even after the syllabus also, after they have released the syllabus, even after that, students were really confused about that what to do in P block and what not to do in P block, right? So I would really advise all the students out there that be strict to the NCERT, stick to NCERT for P block, and basically what you have to do is trends, right? Trends, the electronegativity, ionization, enthalpy, oxidation state, these are the things that you need first. After that, you need to also remember some of the important structures here. That is why I have picked out this chapter from NCERT line by line. We are going to watch all the lines here and see which is important to us and what we can skip. And definitely this is a very important chapter when it comes to NEET exam or any other competitive exam, right? Okay. Hi Sneha, Rohit, Harish, Disha, Madhumati, Pradeep, Roshni, Newton, Madai, Pooja. I think after such a long time, I am taking this lecture. I think after 1 week or so, I am taking the class on NEET English, isn't it? So everybody, green hearts in the chat box for P block. Okay. Today we are going to complete group number 13 and 14. Right, and in the next class we are going to do group number 15 and 16. Then in the third part of this block, we are going to this chapter, we are going to complete group number 17 and 18, and some of the previous year question we will do in the last part, right? Previous year question we will do, but it will be in the last part, that is the third part, right? Okay, yes, because group number 17 and 18 are very small. Group number 13 and 14 is in too much detail in your NCERT. Right? Okay. So your green hearts is going to tell me how much excited are you for this chapter. Otherwise, so I'll see that, okay, these guys are not even excited for P block. Right? Why P block? Because P block is the most demanded chapter. Right? Students crave for this chapter because they're not able to understand that what to do, what not to do from this chapter. That's why I'm saying that P block is the most demanded chapter. So be happy, be grateful, and let us start this chapter with the full power, energy and josh. Okay, yes, okay, so let us start this chapter. The first thing that we are going to do here is what exactly is P block, right? So if we talk about P block here, this is the periodic table, right? This is the periodic table, right? This is how periodic table looks like. And here you have one more block. Now, what exactly what we have, right? First two elements of this are called S. First two groups are called the S block. Here from 3 to 10, 3 to 12, it will be called as D block. From 13 to 18, right? This is from 3 to 12. This is 1 and 2. This is from 13 to 18. That is called the P block, and this is called F block, right? We have D block and F block in detail that we have studied, right? That is in your 12th class. We have already studied from NCERT line by line. Those students who have not watched it, go and watch it because it's a very important thing that I have covered from there, right? Okay. Then S block used to be in your syllabus, but now it's not in your syllabus. So for S block, what are the exceptions that you need to remember that are mentioned in your periodic classification? That is in class 11th, right? You have a chapter called periodic classification, classification of element and periodicity, right? So from there you can count, you can see that what are the exceptions from the S block. But now P block is in detail in your syllabus. If you talk about NEET exam, right, in NEET syllabus it is mentioned that you have trends, electronic configuration, that is mentioned there. But they have not mentioned all the compounds of P block, right? But still we will do some of the things of those compounds. We will not talk about the reactions that much. Reactions you don't have to remember that much, but we will talk about the structures in detail. Okay, right? Now let us start this chapter, P block, right? So now P block elements are the last electron enters in the outermost P block. Like you have the electronic configuration with the last electron enters the P block, that is called P block elements. As we know that number of P orbitals is 3. Okay, how come we are saying that number of P orbitals is 3? Right, for P orbital we make 3 boxes here and 2 electrons are filled everywhere. Right, if you want to fill the electron, it should be like this. So 2 electrons are filled everywhere. So total it has 3 orbitals, right, and it has 6 electrons are filled here, right? Okay, so what we can say here, that 6 electrons and the number of electrons that can be accommodated in a set of P block is 6. Consequently, there are 6 groups of P block because 6 electrons can be filled. That is why it has 6 groups here. For example, if you talk about 3P, 3P1, 3P2, 3P3, 3P4, 3P5, 3P6. So this will belong to group number 13, this to group number 14, this to group number 15, this to 16, this to 17, this to 18. Right? Okay, that is why we have 6 groups in the P block. Right? Okay, next is, now we are going to classify that is from group number 13 to 18. Boron, carbon, nitrogen, oxygen, fluorine and helium, they are the first elements. Right? They are the first elements of all the groups here. Right? For example, boron will belong to group number 13. Right? Carbon belongs to group number 14. Nitrogen belongs to group number 15. Oxygen belongs to 16. Fluorine belongs to group number 17, that is halogens. And helium belongs to noble gases, that is group number 18. So these are the first elements of all the groups that are there in the P block. Right? Their value shell electronic configuration, they are saying it is like this. This is the general electronic configuration. Right? Where S is 2, right? And P varies from 1 to 6, right? That I have told you here. If it is 1, so it is 13, 2, 14, 3, 15, 4, 16, 5, 17 and 6, 18, right? Then we have electronic configuration. Now they are saying that except for helium, because helium has, what is the electronic configuration? Hydrogen, helium, it is 1s2, but still it is in the P block, right? So that is the exception that helium has, right? Now, the inner core of the electronic configuration may however differ, right? Inner core, they are saying that these electrons before this, before NS2, for example, I am saying you have 1s2, 2s2, 2p6. You have 1s2, 2s2, 2p6, 3s2, 3p3, right? So both will belong to P block, right? Because last electron is in the P orbital. But here inner core electrons are these, here inner core electrons are these. That means inner core electrons may differ in this, right? Okay. Next is the difference in inner core electron element greatly influence the physical properties, right? That is atomic and ionic radii, ionization enthalpy as well as chemical properties. Consequently, a lot of variation in the properties of elements in group P block is observed. Right? So that is what we are going to study throughout this chapter, right? That you are going to study the different properties, right? How come we are going to study the trends here, how they vary, right? That is because of the inner core electron. the maximum oxidation state shown by p block elements is equal to total number of valence electrons. Now they are saying how many electrons maximum can be lost or gained. That is equal to total number of valence electrons, right? So students, if you talk about group number 13, right? Valence electrons is ns2 np1. So maximum how many electrons there are in the valence shell? This is the valence shell. So maximum electrons are 3 electrons. That is why in group number 13 you will see 3 positive is the charge on the ions. Why? Because this is the oxidation state, right? This is the maximum oxidation state in which it can exist, right? So this is what they are saying, that the maximum oxidation state shown by p block element is equals to the total number of valence electrons that it is having, right? If you talk about group number 14, it is ns2 np2, right? It is ns2 np2. Now the maximum electrons that it can lose is 4, right? That is why for group number 14 means when we talk about carbon, silicon, carbon forms 4 bonds, silicon forms 4 bonds, right? That is why, because they can lose or gain 4 electrons, right? But here we know that in group number 14, instead of losing or gaining, it will share the 4 electrons, right? What about group number 13? It will be easy for it to lose electrons. So it will lose these many electrons. If you talk about oxygen here, that belongs to group number 16, right? So what it will be? ns2 np4, right? So here the number of electrons that can be lost is 2. Number of electrons that can be lost is 6, right? But now it has 2 choices. It wants to complete the octet here. So instead of losing 6 electrons, it will say that I want to gain 2 electrons and become ns2 np6, because everyone on this planet wants to be stable. Even you are studying because you want to be stable, right? So that is why this group number 16 elements also want to be stable. That is why they will gain 2 electrons. When someone is gaining the electron, they will become 2 negative. That is why you see this thing, right? O2 negative, S2 negative. These are the group number 16 elements, right? Okay. Next is clearly the number of possible oxidation state increases towards right in the periodic table. In addition to this so-called group oxidation state, p block elements may show the oxidation state which normally does not exist, not necessarily differ from the total number of valence shell electrons. They are saying that we are saying that okay, this is the general oxidation state that it will show, but it can also show other oxidation state apart from general oxidation states. The important oxidation state exhibited by p block element are shown in table 11.1. So let us see that firstly, right? This is the table. As you can see here, we will see the different oxidation state that is shown here. Are you able to see the content here? Wait a minute. I think now it is more visible. General electronic configuration and oxidation state of p block. So now let us see firstly group number 13. It has ns2 np1, right? First element is boron, right? Because it is having 3 electrons, so 3 electrons will be lost here, right? Now for group number 14, it is having 4 electrons, so 4 electrons will be lost here or gained here, but it will be shared in case of group number 14, right? If you talk about nitrogen, right? Now see this very carefully, right? That here we are writing that the group oxidation state is +5 because the number of electrons that it has is 5. In oxygen, it is 6. So we are showing that the group oxidation state is +6. Here it is showing 5 + 2, that is +7. Here it is 6 + 2, that is +8, right? Now we will see, we are talking about the group oxidation state. But in reality, what will happen? Let's talk about that. In reality, group number 13, other oxidation state that can occur here, that is +1 also, right? It can also have +1 oxidation state. If you talk about group number 14, it can also have +2 oxidation state or -4 oxidation state, right? Group number 15 can have +3 and -3 oxidation state. Group number 16 can have +4, +2, -2 oxidation state. This though we have observed it in case of oxygen also. Then we have group number 17, +5, +3, +1, -1. These are the different oxidation state which can occur, right? Which is very rare, but it can happen, right? If you talk about group number 18, that is +6, +4, +2. These are the oxidation states that are apart from the group oxidation states, right? Okay, yes. Now visible, I think now it's better. Okay. Next is, in boron, carbon, nitrogen families, the group oxidation state is most stable state for lighter elements in the group. Now they are saying the lighter elements. For lighter elements, tell me one thing, down the group size increases or decreases? When we are moving towards along the period, the size will decrease. Down the group, size will increase. That means the first element is the lightest element, right? The first element is the lightest element. Now they are saying that in this family, the group oxidation state is most stable, very important line, for lighter elements in the group, right? That means the group oxidation state, that is +3 for group number 13, it is more stable above the group, right? That means for boron, aluminium, it is more stable. Down the group oxidation state will become less stable, right? So this is an important line, right? We will talk about this line in when we will talk about in detail in groups also, this line will be elaborated, right? However, the oxidation state 2 unit less than the group oxidation state become progressively more stable for the heavier elements in each group. That means as you go down the group, right? As you go down the group, you can write here down the group. And these lighter are the first elements, right? So down the group, they are saying that the oxidation state that is 2 less. For example, if you talk about group number 13, 2 less means +1 oxidation state is more stable down the group. Okay, so let us again see the table here, right? So this is 2 less. So this is 3 minus 2 is equals to 1. Here it is 4 minus 2 is equals to +2. That means here +1, here +2, here it is +3, here it is +4, here it is +5, here it is +6. So these oxidation states are more stable for heavier element, and these oxidation states that we have written here, that is a group oxidation state, these oxidation state that are the group oxidation state are more stable for lighter elements, okay, that are more stable for lighter elements, right? Now next thing is I think that we have done the occurrence of oxidation state 2 unit less than the group state are sometimes attributed to the inert pair effect, that also we are going to see in detail what is inert pair effect. Don't worry, right? Just relax right now. We are going to see in detail what is exactly inert pair effect. I will give you a hint. It is related to lengthenoid contraction, similar to lengthenoid contraction. Okay, so now let us talk about this. The relative stability of these two oxidation state, group oxidation state and 2 unit less than the group oxidation state, may vary from group to group and will be discussed at appropriate places. As I told you, this we will discuss in all the groups in detail, right? It is interesting to know that the non-metal and metalloids exist only in P block of the periodic table, right? When we were doing periodic classification, there I told you that only in the P block. In transition also, we will see metals, right? If you talk about S block also, there we will see metals. In F block also, we will see metals. But in P block, you have metalloids, you have metals, you have non-metals, right? The non-metallic character of element decreases down the group, right? This, have we seen that in classification or periodic classification, right? Non-metallic character will decrease down the group, right? Metallic character will increase down the group, right? In fact, the heaviest metal in each p block, that means as you go down the group, we know that down the group size will increase. We are saying that non-metallic character decreases, right? That means the heaviest metal, right? Because size is increasing, this is the heaviest metal. Heaviest metal will have the maximum non-metallic character. Sorry, the minimum non-metallic character, right? The heaviest element in P block is the most metallic in nature. That means the least non-metallic in nature, right? You just have to know these two things, that size will increase down the group because here the element that is present here has maximum size, non-metallic character is decreasing. That means this is least non-metallic and it is maximum metallic in nature, right? Okay. Next is this change from non-metallic to metallic character brings diversity in the chemistry of these elements depending upon the group here, right? So in general, non-metals have high ionization enthalpies. Now tell me, what was ionization enthalpy? I am just recapping that thing for you. So ionization enthalpy was to lose the electrons, right? So non-metals, right, they find it very difficult. Non-metals want to gain the electrons, right? So non-metals have a high ionization enthalpy. Why? Because if it is impossible for that atom to lose one electron, right, it will be very electron negative. It will be a good non-metal, right? A metal is electropositive in nature. It wants to gain the electron, right? So a non-metal have high ionization enthalpies, right? And higher electronegativities, as I told you, because they don't want to lose the electron than the metals, right? Hence, in contrast to metals which readily forms cations after losing the electrons, metal, definitely you must have seen that halogens, right? Halogen you will see because it is a non-metal. It will exist in Cl negative, F negative, Br negative. Oxygen will exist as O2 negative, S2 negative. Why? Because they are non-metallic in nature. They want to gain the electrons, right? They don't want to lose the electrons. But if you talk about metals here, then you will see magnesium 2 positive, calcium 2 positive, right? Why so? Why you have seen this as cations? Because they want to lose the electrons, right? Okay. So here we can say that cations non-metallically readily form anions. The compounds formed by highly reactive non-metals, right, that are on that side, right? Because non-metallic character, I'll tell you, non-metallic character, it will decrease down the group and it will increase along the period. Non-metallic character, that will decrease down the group, it will increase along the period. So fluorine is very electronegative, it is very non-metallic in nature, right? So non-metallic with the highly reactive metals are generally ionic. Now they are saying that if you have a cation which is highly metallic in nature, right? If you have a non-metal that is highly non-metallic in nature. So if you have a cation, if you have an anion, this is cation, this is anion, this is very metallic, this is very non-metallic. So because of this, what will happen? Because this B is very non-metallic. Non-metallic means it wants to gain the electron. This is very metallic, that means it wants to lose the electron. So one wants to gain the electron, the other wants to lose the electron. That is why they will have a very strong force between them, that is called the ionic force. That also we have done in chemical bonding as well, that the metals and non-metals together will form a ionic bond, right? Next is, on the other hand, compounds formed between non-metals themselves. If you have compounds between two non-metals, they are largely covalent in character because of small electronegativity difference is very small difference in their electronegativities, right? The change in non-metallic to metallic character can be best illustrated by nature of oxides they form. This we will study in detail. The non-metal oxides are acidic, neutral, whereas this is basic in nature. This all we have done some of the part in chemical bonding. Some of this we will study throughout this chapter, right? Next we have the first member. The first member of P block differs from remaining members of their corresponding group in major respects. So basically, here we will talk about the anomalous behaviors of first member from the other members. Like boron has a very different behavior when compared to the other members of that group, right? That is called the anomalous behavior. First is the size, all other properties which depends on size. The lightest is this. So students, I think we should do in the end only. Why? Because this I will teach you in the end only. Reason being, because here they have concluded some parts, right? They have concluded some parts here. So these till here, firstly we will study all the, firstly we will study group number 13, 14, 15, 16, right? After that, these first 4 pages we will study in the end, because they have given you the summary here, right? Okay, so firstly we will start with the group number 13. After that, we will study what is given here, because all these lines are very important for you. All these lines are very important for you. But this is actually the summary of what we will study in the full chapter. Okay? Yes? Okay, so now let us start with the group number 30. Right? Let us start with group number 30. So guys, let us start with group number 13. Okay? Yes. So group number 13 element, that means the boron family. Right, that means the boron family. So here what you need to learn, first you need to learn the members here. बाल गए इंडियन तेल से. Okay, बाल गए इंडियन तेल से. बाल गए इंडियन तेल से. Right, this is group number 13. Firstly, though, you need to remember the elements here. Right. Firstly, though, you need to remember the elements, then we will talk about the other things. This group elements show a wide variation in properties. Boron is a typical non-metal, right? We are saying that boron is a typical non-metal here. It is not metallic in nature. Aluminium is a metal, but shows many chemical similarities to boron, right? So we'll talk about all the weird behavior, the reason behind that. They're saying boron is a non-metal, but aluminium is a metal, but it has some similarities to boron also, right? To boron and gallium, indium and thallium, right, are almost exclusively metallic in nature. Now they are saying that, and gallium, indium, thallium are almost exclusively metallic in nature, because we know that down the group, metallic character will increase, right? Here metallic character will increase. That means if this is non-metallic, here if the metallic character is increasing, so all these are basically metals, and these are highly metallic in nature. Right? Okay. Next is boron is a fairly rare element, right? Mainly occurs in orthoboric. So these are some of the very, very important compounds in your syllabus. If you talk about, ma'am, do we need to study this orthoboric acid? Yes, this is a very important acid. H3BO3, borax, that is Na2B4O7.10H2O. Then we have kernite. So now, why the formulas are important for you? Because these were there in metallurgy, right, which is now not in your syllabus. But in JEE, last year, what they have observed, that they have asked you questions from these formulas, right? If they can do that in JEE, they can also do that in NEET also, right? Reason being, because you can't say that it is out of syllabus, because it is mentioned in your P block only. So it is in your syllabus only. It's just that it is not mentioned in metallurgy. So that is why you can't skip this particular line here, right? That is why you have to do these formulas as well. That what is the formula of borax, what is the formula of carnallite, right? These are also important for you. In India, borax occurs in Puga Valley. This you don't have to remember, right? And Sambabar Lake, this also you don't have to remember. The abundance of boron in earth crust is less than this much. It is very, not abundant in our nature. As you can see, fairly rare element. There are two isotropic forms of boron, that is boron 10 and boron 11, right? This is 19%, and mostly you will see boron 11. 11 is the atomic mass, right? So 81%. That means boron 11 is the most abundant as compared to boron 10. Next element is aluminium. Aluminium is most abundant metal. As you can see in our house only, you will see everywhere aluminium, right? There are gates of the doors of aluminium, windows of aluminium, even in aluminium foil is we used to use. Now we know that it is not good for our body, right? Earlier though, if you talk about 10 years back, when people had no idea that this is harmful for their own health. Even now, I think in most of the houses they use aluminium utensils only, right? But we should use iron utensils. Why? Because when we cook in iron utensils, that is beneficial for our body. But aluminium, that is not good for our body, right? So that is why that should not be used. Especially aluminium foils, so it should be banned only, right? So aluminium is the most abundant metal and the third most abundant metal in the earth crust, right? That is 8.3 by mass after oxygen, right? It's the most abundant element. And silicon, right? Silicon is 27.7%, right? Firstly, oxygen is very abundant, silicon is very abundant. Then you have aluminium is the third most abundant metal, right? Next we have not element, yes, not metal, element. Bauxite, that is also, the formula is also important for bauxite, right? Bauxite and cryolite. I think cryolite was the question that was asked in JEE. Yes, the question was, I think, related to cryolite, if I remember that. Yes. So these two formulas are also important for you. Are important minerals of aluminium that are found in the earth crust. In India, it is found as mica in Madhya Pradesh and Karnataka, Odisha and Jammu. This also you don't have to remember. We are not giving SST exam here, right? So gallium, indium and thallium are less abundant element in nature, right? So if they ask you which of the, this I think the question of NEET, they have asked you this question in NEET as well, that in group number 13, which is the most abundant element. So in group number 13, you can write it here. As I tell you that why learning inorganic chemistry from NCERT is important for you, just to understand that what kind of question they can ask you. First thing is, from the last two paragraph, what they can ask you directly the question from the formulas of these ores, right? Okay, what is the formula of borax, kernite, what is the formula of cryolite, bauxite, okay, all of these things. And they can ask you most abundant in group number 13. In group number 13, that is aluminium, right? Aluminium is the most abundant in group number 13, right? Okay. Okay, guys. It is audible. Is it not audible? Hello, hello. It is audible, guys. It is audible. Okay, tell me, is this visible? Because I can see that I think it is too white. I don't know why it is too white. Let me see what is the problem. Okay. Audible, no? Yes. Now, next is electronic configuration. So, as you can see, the electronic configuration will be NS2, generally NS2NP1. That is going to be the electronic configuration here. The outer electronic configuration is NS2NP1, and then we will have a close look at the electronic configuration. Suggests that while boron and aluminium have noble gas core, gallium and indium have noble gas plus d electrons, right? Now, if you talk about this thing here, they are saying that if you talk about this thing, this is bal gaye Indian tape. Now, because of these things, no, there will be some trends that will have exceptions, right? What should happen? Down the group, the size should increase, right? But now, because gallium and indium, they have inner core d electrons also, right? So what will happen because of that? Let us see. D electrons cores, thus the electronic structure of these elements are most complex than the first two groups, right, of the elements discussed in unit 10. Now, this difference in electronic structure affect the other properties and consequently the chemistry of all the elements in this group. So now what will happen basically? For example, if you talk about boron and aluminium, they don't have d electrons. Here there is concept of shielding, right? We know that the shielding effect of S, then we have P, then we have D, then we have F. That means D electrons don't have very good shielding effect. Because of that reason, because D electrons don't have very good shielding effect, because of this particular reason, D electrons, right? D electrons will not be able to, what should happen? Down the group size should increase, right? That is the total thing that should happen, right? That means down the group Z effective, that means the nucleus that is inside in the inner core, right? The nucleus should attract the outermost electrons, right? That should happen, right? Okay. So now we are saying that the size is, here the size is decreasing, down the group the size is increasing. So exactly what is happening? Because of the addition of, here it is N, here it is N plus 1, here it is N plus 2, here it is N plus 3. Because of the addition of the overall shell here, if this is 1s, this is 2s, this is 3s, because of this azimuthal quantum number, that is not azimuthal, because this principal quantum number that is increasing because of a new shell that is added here, the Z effective don't have that much power, right? So that is the reason down the group size is increasing, right? But now we have one more effect, that here we have D electrons, right? Now because of these, because this does not have D electrons, this will have D electrons. Because of these D electrons, what are the different effects that it will have, right? We are going to study that. It will affect basically the size, the ionization enthalpy, right? These two things will be majorly affected here, right? Okay. Yes. Now let us see that. First is atomic radii. We are going to see what is the new trend of atomic radii here, right? On moving down the group for successive member, one extra shell is added. That is why the nucleus was supposed to attract the outermost electron, but one new bodyguard is getting added here, right? That is why it is difficult for the nucleus to attract the outermost shell. That is why the size is going to increase here. Therefore, atomic radius is expected to increase. Now, something will happen here. However, a deviation can be seen. Atomic radii of gallium, saying that it was supposed to be this thing. It should increase. It was supposed to be this thing. But atomic radii of gallium is less than aluminium. They are saying that gallium is less than, that means variation that you can see is on this side, right? This can be understood from the variation in the inner core electron configuration. Now basically here we are talking about the screening effect. Now we are saying that the D electrons have poor shielding effect, right? They are not, these are the D electrons, right? This is the outermost electron, right? We know that the size is increasing, that is for sure, right? That is for sure, the size is increasing. Now, what should happen in detail? What should happen? These D electrons that we have added here, right? It is having a poor shielding effect, right? Because of the poor shielding effect, it is not able to, you can say this is the outermost electron, this is the inner core electron, right? These D electrons that we are adding in the D block, right? They are not able to shield the inner core electron here, right? That is why the size is being decreased. Understood one thing? Okay, I'll draw a diagram for that. For example, this is your aluminium, right? These are the, I'm just taking a random example here, right? So this is the outermost electron, this is your parent, this is the outermost electron, right? So when we add the D electrons here, this is nucleus, this is again your siblings, and this is the friend that you rely on, and this is you, and this is you, and this is you. Okay, so exactly what we thought, that new shell, we thought that okay, this is aluminium, this is gallium, because it has more number of shell, so the size should be more. This is what we thought, right? But in reality, what happened? Because these D electrons, you can assume that okay, this is when you have no friend, this is when you have a very bad friend, right? Here you had no friend. For example, you have no friend, right? No friends are there, right? To convince your parents for something, right? So now this nucleus was thinking, this electron, this outermost electron was thinking that these are my parents. What if I had a friend, right? He must have convinced my parents for to go out, for me to, allow me to some party or something, right? Some school trip maybe. Now you are thinking about that, what if I had a friend, right, who could have convinced my parents? But in reality, if you have a bad friend, right, like these blue electrons, if you had a bad friend, what he will do? He will not say, okay, auntie, please send him to, he will like, auntie, please don't. Okay. He should sit there in the house, locked in the house, because he do this, that in the school. He will like gossip about you, right? These are like those bad friends here, right? We were thinking that the size should increase because extra shell is added here. But in reality, because of their poor shielding effect, they are not able to shield this electron from the nucleus. That is why what we were thinking is actually opposite. And in reality, what happened? Even though it had more shells here, the size decreased, right? The size decreased, right? Okay, this is what happened in this case, right? Is this clear to everybody? What we were thinking is actually not what happened here. In reality, we were thinking that gallium has more size because number of shells are increasing, but because of the poor shielding effect of the d electron, gallium has, aluminium has more size as compared to gallium, right? Okay, aluminium has more size as compared to gallium. Now let us talk about this thing. Atomic radius of gallium is less than that of aluminium. This we have talked about, right? This is due to the poor shielding effect of d electrons. As you can see, presence of additional 10 electrons, poor screening effect they are providing, right, from the increased nuclear charge in the gallium. Consequently, the atomic radius of gallium is this one, is less than that of aluminium, right, which is 143 picometer. Now, next is ionization energy, right? If you talk about, is there any effect on the ionization energy? Definitely there is effect on the ionization energy as well, right? So we know that the ionization energy value as expected from the general trend, that is opposite, right? Down the group, ionization energy will increase. So basically, decrease, right? So it should be, wait a minute, it should be this thing, right? That down the group, the size is decreasing, not the size, the ionization energy is decreasing. This was our thought that this should be the trend, right? The ionization energy values are expected from general trends to do not decrease smoothly down the group, right? Actually, they do not smoothly decrease. There will be some variation that you will see. The decrease from boron to aluminium is associated with increase in size. We know that from boron to aluminium, size is increasing. Okay, tell me one thing. What is ionization energy? It is basically the more easy it can lose the electron. So less is the size, it is more difficult to lose the electron. More is the size, it is easy to lose the electron, hence the ionization enthalpy will be low, right? So that means down the group size is increasing. Okay, tell me one thing. When you are near to your house, it is difficult to distract. It is very difficult to distract you, right? Because you have to go by 7 p.m. You have to be in your house. But for example, you are living in hostel, right? That is when we say that, okay, now you are going away from your home. You are responsible for yourself. Why? Because you have seen that most of the suicides, right, that teenagers do, that is not in their house, right? Because in house, though, they are under the guidance of their parents, right? But when they are away, maybe because of some trauma related to studies or so many things, right? Suicides happen, some drink and drive case happen, right? Why these things happen? Because they are away from their home and they maybe don't realize that they are responsible for their own life, right? This is what I'm saying, that when you are going away from the home, size is increasing, right? You are away from the home, right? So now the electron, the outermost electron is not attracted to the nucleus to that much strength. So it is easy for that electron. We can easily lose that electron, right? So this is what we assume, that down the group size is increasing. So ionization enthalpy should decrease. That is why we say that ionization enthalpy should decrease. Now we are saying that this is not very smooth, right? Why this is not very smooth, right? They are saying that from boron to aluminium, there is decrease in size, definitely. Increase in size, so definitely there is decrease in ionization enthalpy. Now, from the next thing, the observed discontinuity in the ionization enthalpy values between aluminium and gallium and between indium and thallium are due to inability of d electrons and f electrons. So now see one thing. Here d electrons are added. Here f electrons are also added. And the shielding effect is like this. S, then P, then you have D, then you have F. That means F have the least shielding effect. It has the least tendency to protect the outermost electron from the nucleus. Just think electron as yourself, right? You are the electron, nucleus are your parents, right? You want to go to some trip to Shimla or maybe Manali, to maybe Ooty, right? Anywhere you want to go. Now, for you to go there, some friend has to come to your house. They have to convince. Now, if that friend is S orbital, then they are good friend. P orbital is not that much of a good friend. D is a very bad friend. F is that friend. F is not even a friend. It's like an enemy only, right? It has worst shielding effect, right? What it will do, if you have F electron in between, if I say here you had F electron, then what would have happened? If here you had F electrons, then what would have happened? Right? For example, here you had, these are the F electrons. Now what would have happened? Because these are the F electrons, right? Here you had the D electrons as well, right? Both have very poor shielding effect. Because of that, this outermost electron is getting attracted towards this nucleus, and that is why it is difficult for this electron. It is difficult to lose this electron. That is why the ionization energy increases here. That is why the trend will be opposite, right, of what we have expected here, right? So this is what they are telling you. Inability of D and F electrons, which have low screening effect to compensate the increase in the nuclear charge, right? Nuclear charge are your parents, right? Parents are saying, I don't want you to go. And your D and F electrons, they are very poor friends. They are not able to compensate with the arguments that your parents are putting up, right? Okay. Okay. So now the order of ionization enthalpy as expected is this. The sum of three ionization. Wait a minute. Let me see if they have mentioned any trend here. Okay. So let us write the trend here. Basically, till here it is same. But what you will observe, that between aluminium and gallium, wait a minute, enthalpy, the discontinuity, the ionization enthalpy values between aluminium and gallium and between indium and thallium. Basically, here you will see, this is actually related to W. Okay, I'll show you how to write the values here. Wait a minute. Okay, these are the values now. This is basically represented like this. W. By a W, you need to remember that, right? So by a W like this. Okay. So, wait a minute. Okay. So here, as you can see, this is your boron, right? Where is the ionization enthalpy? I'm only talking about the first ionization enthalpy. This is the ionization enthalpy, right? From here, you can write the trend, then I will tell you the trick here, right? So as you can see, boron has the maximum, right? Then what you have after 801, you have 589, right? That is because this is weird trend, little bit weird trend. Then you have after thallium, what you have? After thallium, what you have? You have 579, that is gallium, right? After gallium, you have aluminium, right? Then you have indium, right? So now I'm going to draw this W, right? Okay. So this is okay. So after B, you have thallium, right? So these are the W, right? This is the trend. This is how you need to remember the trend, right? This is boron, because this is a weird trend, okay? And that is why this is asked to you, right? Maximum is boron. After boron, you have thallium, right? After thallium, you have gallium, right? Gallium. After gallium, you have aluminium. After aluminium, then you have indium, right? So from this W, you need to remember the trend of ionization enthalpy, right? The trend of ionization enthalpy, you have to remember this from this W, okay? Organic, so we have already completed, huh? Where you are? Organic, though, it is done and dusted. Okay, understood this thing? This is how you need to remember. This is a very, very important trend, right? It's a very, very important trend. Very, very important trend, right? This is for first ionization energy. Okay, this has been frequently asked to you, right? Next is, let us see this. This too we have done. The order of ionization enthalpy, now they are talking about first, second, third ionization enthalpy. Obviously, if you have a metal, right, then to lose one electron, it will become M positive and then it will become M2 positive. So, to lose one electron from a neutral atom is still easy as compared to a cation. That is why the ionization energy first is always less as compared to ionization energy of second, as compared to ionization energy of third, right? But there will be some exceptions. If after losing the second electron, you are getting a very stable electronic configuration, then obviously the second ionization energy will be less as compared to the first, right? But this is the general trend that you need to observe. The sum of three ionization energy for each of the element is very high. Element of this will apparent when you study their chemical properties, right? Okay. So then we have electronegativity. So again, electronegativity is along the period. If you observe along the period, it will definitely increase. Electronegativity increases, and down the group electronegativity decreases, right? So now let us see the trend here, right? So down the group electronegativity first decreases from boron to aluminium, then increases marginally, right? That means these are the general trends. But if you talk about the trend for group number 13, firstly it will decrease from boron to aluminium, then it will increase, right? Okay, that is the trend. This is because of the discrepancy in the atomic size of the element and also the ionization enthalpies. So as you can see here, right, let me tell you where is the electronegativity. This is the electronegativity. So it has decreased here, as you can observe here. It is decreasing. Then again it is increasing, right? So that is, this also they can ask you that in group number 13, what is the trend of electronegativity? So you can write here the trend of electronegativity, that firstly what you will have, firstly boron, then you will have aluminium, right? After that you will have thallium, then you will have indium, then you will have gallium. That is the trend, okay? That is the trend of, wait a minute, indium, then you will have gallium. That is the trend of electronegativity. Firstly it will increase, then it will decrease. So instead of learning the trend, I would say just remember first 2 points, it is increasing, then it is decreasing. In the ionization enthalpy, the trend is very weird. It is, firstly it is decreasing to a large extent, then it is increasing, then again it is decreasing, then again it is increasing. That is why this is a trick for you, because that is difficult to remember, right? But this electronegativity is very easy to remember, right? Okay. Then let us study this chart. Electronegativity we have done. This is ionization enthalpy. As you can see, ionization enthalpy is also increasing. This is first, this is second, this is third. First, second, third. First, second, third. First, second, third. First, second, third. Always first ionization energy is less, then you have second, then you have third is the maximum, right? Okay. Okay. Now, this was the atomic number that you know. Atomic mass also very easy. Electronic configuration, 1 electron always you will have in the outermost shell, right? It's just that the number of shells are increasing here. Atomic radius, we have already seen the variation of atomic radius. Here also you can write the variation of atomic radius, right? Because from table the questions are asked. Firstly, what you have? Firstly, the atomic radius, you have maximum is for thallium, right? Then you have indium, then you have gallium, right? Not gallium. After thallium, you have aluminium, then you will have gallium, then you will have boron, right? This is the weird trend that you will see here, right? Okay. Then we have also talked about atomic radius. Then there is ionic radius, right? In the similar way, then we have ionic radius of M2 positive. The trend they will not ask you in the ionic radius. They will ask you the trend in case of atomic radius, right? In case of ionization energy, they will ask you the trend, right? Next is for density. As you can see, density is increasing only, right? So you can see here, density always increases down the group, right? Density, the heaviness is increasing. Then melting point, what you can see here, everybody in the chat box, I'm just going to copy paste this slide and write down the melting points also here, right? Okay. Because tables are definitely important for you, right? So just write down here, density, it always increases down the group. Increases, there is no exception in this. Increases down the group. If you talk about melting point, and boiling point, right? If you talk about melting and boiling point is, it is firstly decreasing, again it is decreasing, then it is increasing, then again it is increasing. So if you want to write the order of the melting point, maximum is for boron, right? Then we have aluminium, right? After aluminium we have thallium, right? Then we have indium. Then last one is for gallium. That is the order of melting point here, right? If you talk about the order of boiling point, what is the order of boiling point? This is the boiling point. Boiling point is decreasing, again decreasing. So you can write simply here, decreases down the group. These are the little questions that they can ask you, right? Okay, directly from the tables. This is not mentioned to you in any theory. This is directly from the table, right? So this also we have done, this also we have done, right? Okay, E0 potential, they will not ask you. Okay, got it everybody? Yes. Now is the physical properties. Now let us see the physical properties we have already done in the table, but now let us see the theory part here, right? Boron is non-metallic in nature. Rest of the elements are metallic in nature. It is extremely hard and black colored solid, right? It exists in many allotropic forms due to very strong crystalline lattice. Boron has unusually high melting point. Can you see? Boron has a melting point is 2453 and they are below 1000. They all are below 1000. But for boron, the melting point is exceptionally high, right? It is exceptionally high, right? Okay. Because of this strong crystalline structure, right? Rest of the members are soft metals with low melting point and high electrical conductivity. That means current can pass. Good metals means current can pass through them, right? So it is worthwhile to note that the gallium with usually low melting point. Now we know that gallium can also, it can be, when we even keep it in our palm, it can also melt even in the hands, right? It has such low melting point, right? This so you have studied even in lower classes, right? So gallium has a very low point, a very low melting point. It can even melt in our hands. It has such low melting point, right? Okay, yes, don't worry, I'll drink, don't worry. Okay, now next is rest of the members are soft metals. So done. Could exist in liquid state. Now they are saying could exist in liquid state during summer, right? It has such a low melting point. It can exist in liquid also. Its high boiling point makes it a useful material for measuring high temperature, right? So basically, if you talk about the boiling point, they are saying, right? So because of the boiling point, it has very high boiling point. That is why it is useful for measuring high temperature, because it will not be boiled, right? If you want to measure some temperature at a very high temperature, you want to measure something, right? So you will use this metal. Why? This non-metal. Why? Because it has really high boiling point, right? So its high boiling point, it is 2676. Where is it? 2676. They are talking about gallium, right? So 2676. So basically I am writing it here only. Melt in palm used in melt in palm. This I am writing here. Here I am writing because of gallium, it has very high boiling point. We are not saying it has high boiling point apart from these two. Wait a minute. Boiling point is also have a very, okay. Yes. Now, because of its high boiling point as compared to the melting point, right? The melting point was 303, which is really low, right? 273 Kelvin is the room temperature. 303 Kelvin is the melting point. But the boiling point is high only, right? Okay, that is why it is used to measure high temperatures, right? Density of elements increases down the group from bottom to boron to thallium, right? So here the two important points are regarding gallium, its low melting point and its high boiling point, right? Okay, that is about the gallium we have discussed here. Next is the chemical properties. Here you will see a lot of reactions over here, right? So let us see that oxidation state trends in chemical reactivity due to small size of boron. We know that boron has a very small size. That is why it will show some anomalous behavior as well. The sum of its first reionization therapy is very, very high. Now this question has been asked. This question is your question. I think that is in NEET only they have asked these questions, right? Due to a very small size of boron, sum of its first three ionization therapy is very high, right? Okay. Because of the small size, it is very difficult to lose the electrons, right? Because outermost electron is very close to the nucleus, right? That is why the first three ionization therapy are very high. This prevents it from plus 3 ions and forces it, very, very, very important line, that why boron forms covalent compounds, right? This prevents it to form plus 3 ions and forces it to form only covalent compounds. It's a question that is highly asked in your NEET exam, right? Okay, it is like from your NCERT only, it is highly asked in your NEET exam. You must have seen this like so many times, right? But as we move from boron to aluminium, the sum of first reionization enthalpy are not that much high, right? And therefore, you will see that there are aluminium ions that exist. You have not seen B3 positive. Have you seen anywhere B3 positive? Throughout chemistry, I have not seen, right? B3 positive does not exist. Al3 positive exists, right? In fact, aluminium has high electropositive metal. That means aluminium is a metal. It is electropositive. It wants to lose the electron and become cation. However, down the group due to, very, very important, and out of these also, if you talk about these 6 elements, this will form covalent, this will exist in Al3 positive, but down the group, its tendency, like we know that down the group electronegativity decreases, right? So what exactly will happen? Wait a minute, electronegativity decreases, yes. So down the group, what will happen? Down the group, due to poor shielding effect of the intervening d and f orbitals, the increased effective nuclear charge holds ns electrons more tightly. That is why, which is inert pair effect, that is why restricting their participation in the bonding. So you must have seen that for gallium, for thallium, for indium, it is difficult to make the ions. Why? Because of the inert pair effect. Now here we have d electrons. Here we have the participation of d electrons. Here we have the participation of d electrons and f electrons. Because of that thing, it is very difficult for, because of the inert pair, the inner electron, right? They are not able to protect the outermost electron from the nucleus. That is why the outermost electron got attracted to the nucleus. That is why here what will happen, it is very difficult to lose the outermost electron. That is why it is very difficult to lose the electrons and become the ions, right? Okay, understood? As a result of this, only p orbital electron may be involved in bonding, right? Hence, only p orbital, that means the outermost, are only involved in bonding. In fact, in gallium, indium and thallium, both +1 and +3 oxidation states are observed, right? So now what they want to say, that what you have NS2, you have NP1. These are the outermost electrons. These are the outermost electrons. I told you that if you have poor shielding effect, we know that D and F or electrons are very poor shielding effect. That is why they are not able to, the nucleus is able to attract the outermost electron. That is why these outermost electron, it is very difficult to lose them, right? So that is the reason. Definitely, if it will have, sometimes it will show +3 also, but in most of the cases, the p or electrons can get lost. Why? Because it is still more outer as compared to s orbital, right? This is s and this is p, and these are the nucleus, these are the outer, these are the electrons. For example, this is the nucleus that is attracting, these are the d electrons, right? And this is s and this is p, right? So we know that these electrons and these electrons, right? They have poor, these are d electrons, f electrons, they have poor shielding effect. That is why the electrons are getting attracted toward the nucleus. But because it is more closer to the nucleus, it is difficult to lose the s electrons. But p electrons, still we can see that it is difficult, but still we can lose it, right? That is why it will exist in both +3 and +1 oxidation state, right? Okay. Now, there is also this thing that which state is more stable. That question is also frequently asked, right? The relative stability of +1 oxidation state. That means the lower oxidation state progressively increases for heavier elements. So for this, a simple line you need to remember throughout this chapter, P block, that is lower oxidation state increases down the group. Every element, every group will have two oxidation state. One is higher oxidation state, other is lower oxidation state. But the lower oxidation state will have, lower oxidation state increases, it will increase down the group, right? Okay? Okay, guys? Okay. I didn't saw Baswa sir, I just saw him. Hello, Baswa sir. Hello. Yes. This is dating bond. Yes, definitely. Covalent bond. They are dating with each other. Yes. Ma'am, very busy in teaching. Diksha ma'am and Diksha sir on the same platform, right? On the same live. Isn't it? You guys. Now, I think we need to give you some another meme. Otherwise, so I'll die with this Diksha ma'am, Diksha sir thing only. Okay. So now let us see this, because the chapter is really big. No, that's why my full concentration is on the board. Now, this is +1 is predominantly, whereas +3, that is a higher oxidation state, is highly oxidizing in character, right? So down the group, that means boron, that is higher oxidation state. Boron will exist in +3. But down the group, +1 oxidation state will have more stability, right? In the trivalent state, the number of electrons around the sentimental atom in a molecule of the compounds of the elements, for example, boron is Bf3. Now, I told you boron will form a covalent bond only, right? You will see a covalent bond here. Will be only 6. Now, here is another important thing about boron. That if you talk about boron, BCl3 also, 2 electrons here, 2 electrons here, 2 electrons here. That means the outermost electron is 6. It should have outermost electron as 8. That means it is electron deficient. That is why you will see BCl3, BF3. All these are electron deficient compound, and they are called as Lewis acids because they are electron deficient in nature, right? So that is why will be only 6 such electron deficient molecules. They have the tendency to accept the electrons. That is why they are called Lewis acids here. The tendency to behave as Lewis acid decreases down the group, okay? It decreases with increase in the size. That means down the group, the tendency to behave as Lewis acid, it will decrease, right? Okay, but the boron compounds are definitely a good Lewis acids. BCl3 easily accepts a lone pair. Now, for example, you have ammonia, that is a base, right? It will have electrons. That is why this boron, which is electron deficient in nature, it will accept the electrons from this base, right? That is why this is acting as acid and this is acting as a base, which is electron rich in nature, right? And hence it will form this kind of compound, right? Okay, now next thing is AlCl3 achieves stability by forming dimer. Now, if you talk about the structure of AlCl3, let us talk about the structure of AlCl3. AlCl3 forms a dimer, right? That means you have Al2Cl6 that forms a dimer, right? Now, interesting thing about this dimer is that, okay, so firstly, in the trivalent state, most of the compounds being covalents are hydrolyzed in water. So they are talking about hybridizations and all. Chalo, no worries, right? No worries. You just need to remember this thing that AlCl3 achieves stability by forming the dimer. Okay? Okay, understood? Because it also has 6 electrons. Now that is why it is existing as dimer. It is not a Lewis acid, right? It completes its deficiency by forming the dimer, right? So here also 1, 2, 3, 4, 5, 6, 7, 8. It has completed the octet by forming a dimer here, right? Now next thing is the trivalent state of most of the compound being covalent are hydrolyzed in water, right? They are saying the trivalent state of most of the compound being covalent, right? That is why they will hydrolyze in water. For example, the trichlorides, right? Trichlorides, for example, you're talking about BCl3, right? When you add water into it, it will be converted to BOH4 negative, right? On hydrolysis, they form tetrahedral MOH4 negative species. The hybridization state, definitely it is basically, it's like this. This is your M1, 2, 3, 4, OH, OH, OH. This is also OH and it is negative. That is why it is having 4 sigma bonds, and that is the reason this is sp3, that is it is tetrahedral species, right? State of element is this. Aluminium chloride, if you talk about aluminium chloride is acidified aqueous solution, forms octahedral species. This is very important, okay? That for aluminium, it forms octahedral species, right? For aluminium, it will form octahedral species, right? Aluminium chloride in acidified aqueous solution form octahedral species, where you will have 6 water molecule attached to it, right? In this, and it is a coordination compound that it will form. In this complex, the 3d orbitals of aluminium are involved, right? That is why I'm saying that it will form a coordination compound here. It will use the 3d orbitals here, right, that were earlier vacant, right, are involved in the hybridization state of aluminium is sp3d2. This is basically based on coordination, VBT theory, right, that why the hybridization is sp3d2. So this they can ask you even in coordination chemistry, that what is the hybridization of AlH2O6, 3 positive. The hybridization is sp3d2, right? Okay. Next is react. Now we are going to talk about the reactions, right? So there are general reactions here. Just go through the reactions once, but you don't need to go to that in that much detail, right? So here, first thing is boron is unreactive in crystalline form. Aluminium forms a very thin oxide layer on itself, right? So on surface of which protects the metal from further attack. That is why aluminium will stay in your house for a longer time. Why? Because it already has oxide layer on it. Amorphous boron and aluminium metal. Right? If you talk about the amorphous boron, not crystalline but the amorphous, and aluminium metal, when it is heating in air to form B2O3 and Al2O3. That means here what we are doing, E is having +3, O is having -2. That is why after cross multiplication it is forming E2O3 kind of oxide, right? With the dinitrogen, now this was with the oxygen. If you talk about dinitrogen, because E is 3 positive and nitrogen is also 3 negative. So 3 will cancel out, they will form En kind of oxide, right? So you don't need to remember or cram this, just remember that the valency is here. This is 3 positive, that is why after cross multiplication this kind of oxide is formed, this kind of nitride is formed, right? The nature of these oxides varies down the group. Boron trioxide is acidic in nature because boron is a non-metal. Non-metal oxides are always acidic in nature, right? And metal oxides are basic in nature. Reacts with basic oxides forming metal borates. Now they are saying that boron trioxide, they will be acidic because boron is a non-metal. When they are reacted with basic oxides, that is metallic oxides, forming metal borates, they will form metal borates. Aluminium and gallium oxides are amphoteric, right? Down the group, the metallic character is increasing. From non-metal to metal they are going. That is why aluminium and gallium, they will form amphoteric oxides. They are not acidic, not basic. They can also behave as acidic oxide, also as a basic oxide, right? Those properties of indium and thallium are basic in their properties. So they can ask you about the oxides here, right? Oxides here. Which oxide is acidic? Which oxide is basic in nature, right? Okay. Next thing is reactivity towards acids. So now let us talk about the reactivity towards acids. If you talk about the reactivity towards acids, right? Boron does not react with acid and alkalines even at moderate temperature, but aluminium dissolves in mineral acid and aqueous alkali, thus shows amphoteric. Very, very important that aluminium is amphoteric in nature, right? With acids also it will react, with base also it can react, right? So aluminium dissolves in this and liberate hydrogen, which is a property of metal, amphoteric oxide, because it is reacting with acid as well as base, right? Concentrated nitric acid renders aluminium passive by forming a protective oxide layer on the surface. This is also an important thing to note down, that this also question is important, that if you talk about aluminium with HCl, H2SO4, it can easily react and liberate H2. But if you talk about nitric acid is a good oxidizing agent, right? So it will give oxygen. That is why on the aluminium you will have oxide layer. That is why after that aluminium will not react with the nitric acid. Understood? This question also can be asked, right? That why aluminium reacts with other acids but not with nitric acid? Because nitric acid is also a good oxidizing agent. Write it down because it is not written in your book. That is why write it down, because nitric acid is a good oxidizing agent, right? Aluminium also reacts with aqueous alkali and liberates dihydrogen, right? Now this forms sodium tetrahydroxyeliminate, right? Basically you can just say eliminate is formed, right? Because of this we can say that this aluminium is amphoteric in nature. Now towards a halogen, how it will react? Towards these elements react with halogens to form trihalides, except for thallium, right? Okay, except for this halide with iodine, except for thallium with iodine. So this question also can be asked, that here E reacts with X2 to form EX3. Firstly, the question is why. Why is E3 positive and X negative? Cross multiplication, you will have EX3. But now here, the exception is that if element is thallium, then halogen cannot be iodine. This is not formed. This is the exception, and from exception only the questions are asked, right? So you can mark it here that which halide is not formed. The halide is thallium iodide is not formed, right? Okay. Exceptions also, they will ask you the questions from the exceptions. Okay. Next is important trends of the anomalous properties. Now anomalous properties, right? Anomalous properties of boron, very important. Let us see the anomalous properties of boron here. From here the questions can be asked, right? Most of the things we have studied before only, right? Certain important trends can be observed in the chemical behavior of group number 13. The trichlorides, bromides and iodides of all these elements being covalent in nature are hydrolyzed in water, right? Species like tetrahedral and octahedral, except in boron, exist in the aqueous medium, right? Now they are saying that what is the anomalous trend that boron is showing? Firstly, boron is very small size. It is showing covalent character, right? All other are showing ionic character. Why it is so? Right? So what are the different characters it is showing? They are saying that trichlorides, bromide, iodides of all these elements being covalent in nature are hydrolyzed in water. Species like tetrahedral and octahedral are formed definitely, right? They are also formed. Aluminium will form octahedral species. But they are saying except in boron exist in aqueous medium. They are saying boron does not form these kind of species, right? Reason: the monomeric trihalides being electron deficient are strong Lewis acids, right? Boron trifluorides easily react with Lewis bases such as NH3 to complete the octet around the boron. Now they are saying that the monomeric trihalides of boron, right? They are very Lewis acid. They are basically Lewis acids in nature. They easily react with base and complete their octet. As you can see here, it is BF3, it is NH3, it is an acid, it is a base. They will react together, right? And they will form a coordinate bond between them, right? Now, here is the reason. These are the questions that they can ask you. These are the reason. This is the reason. Assertion reasoning question can be asked to you, right? They can ask you regarding why boron does not form. It does not get, the trihalides of boron does not get hydrolyzed in water. What is the reason behind that, right? So reason is, it is due to, first thing is absence of d orbitals, right? Absence of d orbitals, right? First is absence of d orbitals. That maximum covalency of boron, this question is, this answer is very, very important. That boron, aluminium, even in aluminium, it does not have electrons, d electrons, but there is vacant d orbital. That is why aluminium can expand its covalency. But boron cannot expand its covalency because there is not even empty d orbitals, right? So it is due to the absence of d orbitals that maximum covalency of boron is 4. Since the d orbitals are available with aluminium and other elements, the maximum covalency expected beyond 4. It can expand the covalency, right? It can form also 6 bonds. Most of the other metals, halides, are dimerized, as we have talked about. That aluminium also, if you talk about AlCl3, it also has 3 electrons, 1, 2, 3, 4, 5, 6 electrons. But here to complete the octet, it will dimerize. But if you talk about boron here, right, to complete the octet, it will not dimerize, right? It will behave as a Lewis acid here, right? This is what they are asking. So most of the other elements, they form dimers, right, are dimerized through hydrogen bond, through halogen bridging. For example, Al2Cl6. The metal species complete its octet by accepting electrons from halogen in these halogen bridged molecules, as you have seen here, right? This is the dimer, right? This is the halogen bond, right, that they are forming here. This is they are acting as a bridges, right? So that is what they are saying, that due to halogen bridges, they are forming a dimer here, right? Okay. So these were the important, this is a very, very important question that is asked to you. Again, I am saying, they will ask you, they can ask you why the trihalide of boron is acting as a Lewis acid and not for others. Why? Reason is it cannot expand the covalency boron, that is why it is acting as a Lewis acid. Why other halides are getting hydrolyzed but not boron? Reason is the same, right? So any of this question they can ask you, right? Why? Simply they can ask you why boron is having an anomalous behavior. Reason is again this, right? Okay. Arey guys, what you need break for, yaar? In the exam hall, you're going to give, going to give test for 3 hours. Are you going to ask them, please give me break for 5 minutes? You will not get it, right? So have that tendency in your head that your mind should be capable of studying for 3-4 hours, right? On straight. If I can stand here and talk about 3-4 hours, then you can definitely study, right? After 2 hours, I'm going to definitely give you the break. Now, next is the compounds. Let me complete at least group number 13. After that, I will give you the break, right? Now, these compounds, you don't have to do in that much detail, okay? So, I'm telling you that you don't have to do this in so much detail that I'll study each and everything about single. Till here, everything is very important. Till here, things are very, very important for you that have been asked in your NEET exam. But from now, we have to be very selective because they have not mentioned the compounds. But it's not like you will just skip everything here. Okay, don't do that thing that I will skip everything here, right? So let us see what are the selected things that we are going to do. Some important compounds of boron. First is borax, right? The most important compound of boron, it is white crystalline solid formula. Firstly, so you need to remember the formula. Whatever I am highlighting with red pen, that you have to do, right? Borax, firstly, what is the formula of borax? Very important. It in fact contains tetranuclear units, right? These are the units that it contains. Units also you need to remember what are the units that it contains, right? And correct formula therefore is Na2B4O5OH4, right? This is in the units, right? This is the units that you have, right? This is what they are saying, that the exact formula is B4O7. But this B4O7 plus dot 10H2O, it exists as this, that is B4O5OH4 2 negative. They can ask you the question like, what are the units in borax, right? So they can give you 3-4 options, and out of that, this is the correct option, right? Then borax dissolved in water to give alkaline solution. It will dissolve in water. Now, this compound is important. This is borax. It will give you a very important compound, that is orthoboric acid, right? That is also written as BOH thrice. It is actually an acid, but from here students feel that this is a base. It is actually a acid, right? Or you can just simply say it is boric acid. On heating, borax firstly loses water of molecules and swell up. On further heating, firstly on heating, it will lose the water of crystallization, right? It will swell up, right? Give us metaborate. On further heating, it is converted to a transparent liquid which solidified into glass-like metal known as borax bead. So this is basically borax bead test is also done in laboratories, right, to identification of the compounds, identification of the elements in inorganic chemistry, especially in salt analysis, right, we do this borax bead test, right? That is a test called borax bead test, right? From there we use the borax, right? That is why I'm telling you that this thing can be applied in salt analysis as well. So you need to know some of the part of it, right? So exactly what happens, you have borax, you heat it, you have sodium metaborate. After further heating, you will have a thing that is called borax bead, right? Okay, so now the metaborates of many transition elements have characteristic colors. Therefore, borax bead test can be used. This thing is important. Borax bead test can be used to identify the elements in the laboratory. For example, when borax is heated in a Bunsen burner flame with cobalt oxide on a loop of platinum wire, a blue colored bead is formed, right? So you just need to remember the color of this, that when you use cobalt oxide, then blue colored bead is formed. This is called borax bead test, okay? That is called borax bead test. I know so much cramming it has. So I would suggest you don't see any other book except from NCERT. More than enough is given to you, right? Mostly they will ask you questions from trends or from structures or from exceptions. This has very less probability, but still I'm telling you what is important for you, that there is a borax bead test that is that we use for identification of elements, which element is present. For example, for cobalt, there is blue colored bead is formed, right? Okay, right? Next is orthoboric acid, that is important for you, right? So this is H3BO3. Is a white crystalline solid, soapy touch. It is sparingly soluble in water. Then it can be prepared by acidifying solution. Preparation is not that important for you, right? It is also found by hydrolysis with what is most known as boric compounds. It has layer structure. Now structure is important. It has layer structure in which planar BO3 units. In borax, you need to remember the units. These were the units: B4O5, OH4 2 negative. These were the units in borax. In boric acid, you have BO3 units, right? And what is important for you to remember, joined by hydrogen bonds, right? As you can see this in this figure. So one BO, this is one molecule, right? One molecule, wait a minute, one molecule is linked to 1, 2, 3, 4, 5. 5 hydrogen bonds, right? 5 hydrogen bonds. One molecule is linked to 5 hydrogen bonds. And how much is the membered, what is the ring membered, what I'm saying? Okay. How much membered ring is it? 1, 2, 3, 4, 5, 6, 7, 8. It is 8 membered ring. See, you're not preparing for board exams, right? Even in board exam, they will not ask you this, but they can ask you question like in boric acid, right? With one molecule, how many hydrogen bonds are there? So it has 5 hydrogen bonds, right? These are the things that are important for you, right? Then you have 8 membered ring, right? This they can ask you which membered ring is formed. 8 membered ring is formed, okay? You don't have to draw the structure, and that is not important, right? Okay. Now, okay, this also we have done. Now, boric acid is weak monobasic acid. This is also very important. This also we have done in redox reactions as well. It is a weak acid. It is a mineral acid, yet it is a weak acid. And it is a weak monobasic acid. Basically, from here, students feel that it is a tribasic acid. But actually, it is a monobasic acid. That is why this is very, very important for you, right? It is not a protonic acid, but acts as a Lewis acid, right? It is not donating the H positives. It is actually electron deficient. That is why it is electron deficient. Can you tell me? It is not a protonic acid. You can't say that, ma'am, it has 3 hydrogens, so it is tribasic in nature, right? Actually, what happens is it has OH here, simple diagram I am forming, right? So these are the 3 OH groups here. That is why it has 6 electrons. So because it has 6 electrons, it is electron deficient. So that is why it is acting as a Lewis acid, right? You can't say that it is having 3 H positives, ma'am. Why not tribasic? Because it is not acidic because it is donating any H positives here, right? Okay. So it is Lewis acid by accepting electrons from hydroxyl ion. So it is going to accept the electrons and become BOH4 negative. On heating orthoboric acid, above this, the metaboric acid, that is HBO2, which is further on heating yields boric oxide is formed, right? You just need to remember, when you heat boric acid, boric oxide will be formed. That's it, okay? When you heat boric acid, boric oxide is formed, right? Okay. Next is the structure we have done. Next is diborane. Now this diborane structure is very important for you, right? Because it is a very unique structure. That is why it is important. The simplest boron halide known as diborane, right? It is prepared by preparation is not important. Then we have a convenient laboratory method, that is also not important for you. Now, these are all the reactions not very important for you, right? Reactions are not important if you talk about today's scenario, right? But still, let us go through that. Diborane is produced in industrial source by Na. Diborane is colorless, highly toxic with boiling point of 180. This you need to remember. Colorless, highly toxic gas catches fire spontaneously upon exposure to air. It burns in oxygen. Enormous amount of energy is released. Most of the higher boranes are also spontaneously flammable in air. Boranes are readily hydrolyzed by water to give boric acid. Okay, it will give boric acid. This you need to remember, right? That it will give boric acid. Now, next thing is diborane undergoes cleavage reactions. This reaction is actually important for you. This reaction is actually important for you. That diborane, if you talk about diborane, it reacts with nitrogen Me thrice. Now this is methyl group, right? What it undergoes cleavage reaction with Lewis bases. These are the Lewis bases and gives a borane adducts, right? These are the borane adducts, that is BH3 dot L. L is the base. L is the base. So base is NMe3. So it will give you the adduct here. Here it is CO carbon monoxide. So it will attach here and give you the adduct here. The reaction of ammonia with diborane give initially B2H6.2NH2, which is formulated as this thing, right? This is also important. Give borazine. Now this is important for you, right? This whole reaction is important. This whole reaction is important. Why? Reason is we have formation of inorganic benzene. That's what I am telling you. You don't have to cram all the reactions, right? Some of the reactions may be asked, right? You never know. Reactions of ammonia with diborane, it will firstly give you B2H6, adduct will be formed, that is 2NH3. Then it will be formulated as BH2, NH3 twice positive, BH4 negative, which on further heating, it will give us very, very important compound, that is inorganic benzene, that is called B3N3H6, right? Very, very important compound, right? Why this is very important for you? Wait a minute. Where is the structure of inorganic benzene? It's not there. Is it here or not? Okay, it's not here. So I'll draw it myself. So basically, what is benzene? What is benzene? This is called benzene, right? This is called benzene, alternate double single bond, right? This is called benzene. So instead of this carbon, you will have boron, 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 and you will have nitrogen, nitrogen, nitrogen. that is called the inorganic benzene, right? That is called the inorganic benzene. So instead of carbon, you have nitrogen and boron, right? That is why it is called benzene kind of structure, but it does not have carbon in it. Instead, the elements are boron and nitrogen, right? In view of its ring structure with alternate BH and NH groups, right? So B2H6 with NH3, it will firstly give you this compound, right? Then after heating, it will give you B3N3H6, right? That is the inorganic benzene, right? Now is the structure of diborane, which is very important. This so easily they can ask you. And also they have asked you this so many times, right? Because here are different bonds you will have. So basically, what are the different bonds? The 4 terminal hydrogens. This is, they are talking about terminal hydrogen. This one, this hydrogen, this hydrogen. These are the terminal hydrogens, right? So basically, if you want to draw the structure in an easy way, it's like this. This is boron, this is boron, this is 1, 2, 3, 4. 4 hydrogens that are on the terminal positions and 2 hydrogens that are on the bridging positions. These are the bridging hydrogens, right? So now what they are saying, very important, the 4 terminal hydrogen atoms and the 2 boron atoms lie in one plane, right? So if we talk about, this is one plane, boron will lie here and 4 hydrogens will lie here. This is one plane. But the bridging hydrogens will lie above the plane, right? They will lie out of that plane, right? So that is very important. Below this plane, above and below this plane, there are 2 bridging hydrogen bonds that I have mentioned by that blue pen. The 4 terminal BH bonds are regular 2-centered. So very important that what is a 2-centered 2-electron bond? What is a 2-centered 2 electrons? As you can see here, you will have 2 electrons and 2 atoms are there. Here you will have 2 electrons and 2 atoms you will have. Right, here also you will have 2 electrons, 2 atoms, 2 electrons, 2 atoms. So they are saying that the terminal will be 2-centered, normal 2-centered 2 electron bonds, but the 2 bridging bonds, that is BHB, it will have 3 centers. One is boron, then hydrogen, then boron. But the electrons that it will have is 2 only. The electrons will be 2 only. So 3-centered 2 electrons can be described in terms of 3-centered 2 electron bonds. Okay, that can be described as 3-centered 2 electron bonds. Very important. And these are also called banana bonds. This BHB and BHB are also called banana bonds because they are out of the plane. This is the plane, right? One banana will be above it, one banana will be below it. So these are called the banana bonds, right? Okay. Boron also forms a series of hydridoborates. The most important one of the tetrahedral BH4 negative. Tetrahydroborates of several metals are known. Lithium, sodium tetrahydroborates are also known as boron hydrides. Wait a minute, right? Prepared by the reaction of metals. Okay, not very important, but you can just go through that. Okay, not very important. Both LiBH4 and NaBH4, which are reducing agents, are used as reducing agents in organic synthesis. They are useful starting material for preparing of metal borohydrates, right? Okay, understood? LiAlH4, NaBH4, right? So this is what they are talking about, right? Okay. Now this is your structure of diborane, right? Very important. So these are your 2 banana bonds. These are your 2 banana bonds, right? So this is explained over here, which is 2-centered, which is 3-centered, that I have already told you. This is 2-centered 2 electron and this is 3-centered 2 electron, right? Okay, which is also called banana bond. Okay guys, Now let us do the uses of boron. Let us do the uses of boron. Let us do the uses of boron here. Let us do that. So uses of boron and aluminium and their compounds. Boron being extremely hard refractory, right? Uses are also very rarely asked, right? But still we will go through that. Hard refractory solid of high melting point, low density, very low electrical conductivity. Many application boron, because this much theory is not possible for you to learn. So we will pick out the points that they can ask you. Boron fibers are used in making bullet-proof vest. Now this is an important point, that boron is used in bulletproof vest, light composite material for aircraft, right? For aircraft it is used, for light material because it is having a very less mass. The boron 10 isotope has high ability to absorb neutrons, and therefore metal borides are used in nuclear industry, right, as protective shield and control rod. So basically in nuclear reactions they are used because neutrons will be produced in those reactions. To absorb those neutrons, boron compounds are used, basically borides are used, right? The main industrial application of borax and boric acid is the manufacture of very important heat resistant glasses, pyrex, glass, wool and fiber glasses. Heat resistant glasses are used, right? Okay, borax is also used as a flux or soldering metals for heat, scratch and stain resistant glazed coating to earthenwares. Earthenwares means you can say to earthen the conductivity of electrons, right? Okay, so when you say that, is your house is earthened or not, that means the current what if your house is not earthened? That means even if you touch this board, I will feel current, right? So basically that is how earthened things are used for you. So it is heat resistant glasses and also the electrical resistant things, right? Stain resistant gazette coating to earthenwares and as constituent of medicinal soap. This all is not important. An aqueous solution of orthoboric acid is usually used in mild antiseptic. Aluminium uses letter C. Aluminium uses letter C. For here you need to remember two things. One is pyrex, other is nuclear industry, then bulletproof vest, right? And directly they will not ask you the uses, right? I'm telling you directly they will not ask you, right? So now aluminium is a bright silvery white metal. This all we know. High tensile strength. It has a high electrical thermal conductivity. That is why when you put some hot roti, chapati inside that aluminium foil, it will also get very hot, right? On a weight to weight basis, the electrical conductivity of aluminium is twice that of copper, right? It is a very good conductivity, right, of the electricity. Aluminium is used extensively in industry and in everyday life. It forms alloys with copper, manganese, magnesium, right? You must have seen aluminium alloys. Aluminium is its alloy can be given shape to pipe, tubes, rods, wire, plates, foils. This we use in our daily life, in our homes it is used, right? Okay, yes, no, it's not completed. Aluminium and its alloys can be given shape, this and that. Okay. The use of aluminium and its compounds for domestic purpose is now reduced considerably because of their toxic nature, right? We all know that now it is like nobody uses aluminium foil in their house. If you are still using it, then you need to just ban that in your house because it is very toxic for our body, right? Group 14 elements. Now next is group 14 elements, right? Okay, so let me see. Yes, so we have completed group 13, right? I'll give you a break now. After that we will complete group number 14. That is basically carbon family, right? That is basically carbon family. 𝐂𝐡𝐞𝐤 𝐻𝐿, right? Carbon, silicon, germanium, tin, lead. Okay, so these are the 5 compounds that we are going to study, and here the compounds are also very important because We will talk about allotropes of carbon, diamond, graphite, Buckminster fullerene. We will talk about very important compounds of silicon, right? Rest of the compounds are not important for us. The properties are somewhat similar, right? Properties are somewhat similar. You will see similar kind of trends going on in every single group, right? Okay, yes. So now guys, I am going to give you the break here, right? So break is going to be for how much time? What is the time here? What is the time? Time is 8. So I'll be here at 8:10 p.m. Right? I'm giving you 10 minutes break. I'm giving you 10 minutes break. And here you have your break. But before that, I need to show you something. Just give me a minute. Break, ma'am, thanks. Now, wait a minute. Okay. So this is what you have. I hope so you guys are able to see this. Are you guys able to see this? Now, guys, in the description, what you will see that there is get complete NEET preparation treasure box, right? Because we have completed our syllabus, right? So now is the time to go through the notes, practice the questions, right? Do the revision again and again, because more the revision you do, more successful you will be in your NEET exam, right? And more the practice you do, more successful you will be. So in this treasure box, everything is free for you. Just click on that link here that I have told you. Get complete NEET preparation treasure box. Here PDF, PYQs, class notes. What if you have lost some of the class notes? So that are available here. CBSE, NCERT, NEET previous year questions are available to you. As you can see here, if you talk about chemistry section, right, this is the chemistry section. Any chapter, if you talk about, ma'am, I want to see the hydrocarbons. So just click on this thing, right? You will get to the hydrocarbons, all concepts, tricks, NEET, PYQs, everything, right? This will be the link, right? If you want to see the, wait a minute, here NEET PYQs are yet to be uploaded. If you want to see the previous year question test here, just click on that, right? And you will get to this portal. Just fill your mail ID or your number here and you will have your previous year question test. If you want to see what are the NEET previous year questions, again you have to put the mail ID here, right? Then anything that you want to see, chapter wise previous year question PDF, you want to see the class notes here, that will also be provided to you. Everything, the link is given here, right? The link of all the things are provided to you, right? The previous year question PDF is also anything you can click here, right? And then you just need to put it here. Wait a minute, let me, okay, but that's not my number, right? Okay, so now I think that's it. Okay, you need to fill that. Obviously, I'm not going to fill my number here, right? So you can just fill your number or your mail ID, right? And then click on that and you will get to all the previous year question test. You will get to the notes as well, the NEET previous year questions as well, the CBSE, the NCERT solution as well. All the things related to that chapter will be provided to you, right? And that is totally free of cost. You just need to click here on this particular portal, right? Okay, you just need to click here. Okay, Nandu, Soumya, Arjun. Okay, yes. So now I am giving you the break, right? Now I am giving you the break. Okay. So I would advise you, in meanwhile, I am giving you the break. I would advise you that go through that link and download all the important things that you want, right? Because right now it is free of cost. I don't know for how much long time it will be free of cost. Okay, guys. Chalo, now I'm giving you break for 10 minutes and I'll see you at 8:10 p.m. Hello everybody. Am I visible? Am I audible to everyone? Everyone in the chat box, am I visible? Am I audible? Yes, Roshni, Nandu, DJ, Tiger, Abhishek. Good morning. Very good morning. Very good morning. And have a nice day. Okay, so now we are about to do group number 14, right? Okay, so are you all ready for group number 14? It will be quite similar to group number 13 only, right? So let us start with group number 14. So group number 14 means carbon, silicon, germanium, tin and lead. These are the elements that you have in group number 14. Carbon is 7th most abundant element, right, in our earth, right? We know that carbon is everywhere around us. Carbon, coals, diamonds, graphites, everything is around us, right? It has certain amount of carbon, right? Especially the fuels. It is widely distributed in nature as well as in a free as well as the combined form, right? In carbon dioxide we have in an atmosphere. In elemental state it is available as coal, graphite and diamond, right? It is not combining with some other element. But if you talk about in the combined state, it exists as carbonates, hydrocarbons, carbon dioxide, which is present in 0.03% in our air, right? Then one can empathetically say that carbon is the most versatile element, right? Dancing. Versatile element it is. Basically, it is also existing in combined state, is also existing in a very combined state. It is also toxic. It is also okay for our health, right? In our body also it is existing, right? As carbohydrates, we have carbons. Its combination with other elements such as dihydrogen, dioxygen, chlorine, sulfur provides an astonishing array of material ranging from living tissues in our body to drugs and plastics that we see around. Plastics means polymers they are talking about. Polymers are also the combination of so many hydrocarbons, the organic compounds, right? So organic compounds, so definitely they have carbon, right? So living tissues to drug, plastics. Organic chemistry is devoted to carbon containing. In organic chemistry, we talk about carbon and hydrogen containing compounds. It is essential constituents of all living organisms. Naturally occurring carbon contains very important. So it is basically naturally occurring has two isotropic forms, that is carbon 12 and carbon 13. In addition to these, there is also third isotope, that is carbon 14 is also present. It is radioactive isotope, that is carbon 14. That is a radioactive isotope used. It is actually found in nuclear reactions, fission-fusion reactions, with half-life period of 5770 years and used for radiocarbon dating, right? This, so I think you must have seen radiocarbon dating in maybe nuclear physics, right? You must have seen a little bit of what is carbon dating, right? So silicon is the second. After carbon, you have silicon, is the second most abundant. We know that the most abundant, when we talked about aluminium, that was the third most abundant, right? So basically, oxygen is the first abundant, then you have aluminium, then you have silicon. And on the seventh position, you have carbon, which is the abundance of all these compounds, right? So silicon is very important component of ceramics, glass, cement industries. Silicon is used, right? Now, germanium exists only in traces, right? It does not exist in large amount. Tin occurs mainly as, now this is very important, what is cassiterite, right? What is the formula of cassiterite, right? And what is galena, right? What is galena? That is PBS. Very important, right? The name and the formula is very important, and this also has been asked in, I think, JEE, right? In previous year, I think last year only it has been asked. And it was a controversial question also, because students felt that, okay, this was out of syllabus, but actually this was mentioned in your P block, right? So ultra pure form of germanium and silicon are used to make transistors and semiconductors. I think Shreya sir must have taught you semiconductors, N-type, P-type, if I remember, N-type, P-type diodes. I don't remember that much of physics, but yes, something like N-type, P-type, right? Is it so? Diodes, right? I remember that was one of my favorite topics. Semiconductors was my favorite topic. The gates, OR gate, AND gate, right? OR, AND, and I forgot about the other gates, right? So in semiconductors, we know that on adding the silicon or germanium, right, we have different semiconductors, right? We can make it insulators, you know? Something that kind of concept was there in N-type, P-type semiconductors. The important atomic and physical properties of group 14 elements with their electronic configuration are given in that. So let us see that. First thing is the electronic configuration. So it is just add 2 electrons to the p orbital. So it is ns2np2, right? So highest oxidation state is +2. Lowest oxidation state is, highest oxidation state is +4, lowest is +2, right? So what is a covalent radius here? There is a considerable increase in covalent radius from carbon to silicon, right? Thereafter, from silicon to lead, a small increase in radius is observed, right? This is due to presence of DNF orbitals in the heavier members. Now they are saying that here it's not like the order has changed, the order has remained the same, but from silicon, carbon to silicon, it is large decrease. After that there is small increase, right? Okay, wait a minute, let me show you that in the table only. This is the atomic number, atomic mass. Okay, so here it is large increase from 12 to 28, that is double. It is more than the double, right? But after that, there is small increase here, 28 to 72, right? I to consider it as, wait a minute, from which thing to which thing? From carbon to germanium, carbon to silicon, right? Increase, considerable increase. Therefore, after silicon to lead, let me see that. Silicon to lead, there is not that much increase. But here, so we can see that much increase, but that is mentioned in the NCERT, so we have to pick that point only, right? So that according to the values, so it is like considerable increase only, right? But now they are saying that it is not that much large. Okay, wait a minute. So sorry, I was just seeing the atomic masses. Atomic masses, so we know electronic configuration. Let us talk about covalent radius. That's what I was thinking, that how come this is a not considerable increase, right? So here you can see from 77 to 118, right? That is a large increase. If you talk about from 118 to 112, right? It's just an increase of 4 points. Here also it's a considerably small increase as compared to from 70 to 120, right? Again, there is increase of 6 points only. So that means from carbon to silicon, there is large increase. After this to this, there is small increase, right? Okay, so let us see that. Let us confirm that due to the presence of DNF, the shielding, the poor shielding effect of DNF electrons, right? Okay. Then there is ionization enthalpy. First ionization enthalpy of group 14 members is higher than the corresponding. Now here they are saying the first ionization enthalpy of group 14 member is higher than the corresponding member of group number 13. Firstly, there is comparison, right? Here you have group 13, here you have group 14. It is group 13 is NS2NP1, it is NS2NP2, right? So in this case, what you will observe, size is going to decrease along the period, right? That means the size of group 13 is more as compared to group number 14. So less is the size, right? For example, you are living very near to your home, right? You are living in some hostel, but you are living just 1 to 2 hours away from your home. So now your parents can come anytime to your hostel and check where are you. But for example, you are living abroad, Right now, your parents can't just take a flight every day. Now, like if you're Ambani, then they can take the flight every day and check whether what my kid is doing. But if you're like us, middle class, that obviously you can't afford like flight any day, right? So what you will be free there. You'll be like, oh, my parents can't come to foreign country and check what I'm doing, right? So basically, this is your group number 13, like which has a large size. That is why it is away from the parents. So it is very easy to lose the electrons. But here, because of the small size, it is very close to the nucleus. That is why the interactions are more. That is why the outermost electron is very attracted towards the nucleus and it is very difficult to lose it. That is why high ionization energy of group number 14. So ionization energy is more for group number 14. Is that clear to everybody or not? Now, the influence of inner core electron visible here also, right? In general, the ionization enthalpy decreases down the group. This is in general, we know that. Smaller decrease from silicon to germanium to tin and slight increase in tin to lead is the sequence of poor shielding effect in DNA of output increase in the size of this. They are saying that in general this will increase, but small increase in this, what exactly happens here? They are saying that, let us see the table again. Let us see the table again. Where is your ionization energy? This is the ionization energy. Here what we will see, right? Here they are saying it is decreasing, right? Now it is again decreasing. Again it is decreasing. Again it is decreasing. Now, here you can see a large decrease, right? Here you can see 20.2 it decreases. Here it decreases to 60 points. Here again it decreases to less than 20 points, right? So this is what they are saying, that firstly what will happen? From carbon to silicon there is large gap. Then from silicon to germanium, and then from germanium to tin, slight increase. Wait a minute. Here it is decrease. Okay. Then from this to this, there is again decrease, slight decrease. Then here also it is decrease only, no? Here also it is decreasing. From here it is increasing, slight increase. So this is your carbon, silicon, germanium, 𝐂𝐡𝐞𝐤, and this is lead. So basically, here there is large decrement, then very small decrease, then very small decrease, then again a very slight increase that you can observe, right? So overall effect is of DNF, inert pair effect of DNF, poor shielding effect, right? That you can observe here. If you talk about the ionization energy 1, 2, 3, 4, it is definitely increasing, 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 and again increasing. So that means we can say that IE1 is less as compared to IE2, then IE3, then you have IE4 in general, right? Okay. Okay, guys. Now that is your decrement, and from tin to lead is the consequence poor shielding effect. Slight increase in tin to lead, right? This is important, right? Next is poor shielding effect, that also we have done. Now we have the electronegativity, right? Let us talk about the electronegativity. Now electronegativity, usually it will along the period it will increase, and down the group it will decrease, right? Along the period it will increase, down the group it will decrease, right? So we are talking about down the group, so it should decrease. So that means carbon should have maximum electronegativity. Due to small size, the elements of this group are slightly more electronegative. Firstly, we will compare this with group number 13. So we know that along the period, electronegativity increases. So group number 13 definitely has less as compared to group number 14. Now they are saying what is the reason? Due to small size, the elements of this group are slightly more electronegative, right? Then group number 13 elements, right? Now they are saying that because the size is decreasing here. We know that along the period what happens? If you talk about boron and carbon, the size of boron along the period, the size decreases, right? So boron has more size, carbon has less size. Because of less size, the outermost electron is attracted towards the nucleus more. That is why it is difficult for it to lose it, right? That is why it has more electron negativity. It does not want to lose the electron, it wants to gain the electron, right? Then we have then the group number 13, the electron negativity values for the elements from silicon to lead is given here. Let us see it in the table only. Electron negativity value, firstly it will decrease, then constant, constant, constant. This question has also been asked in JEE mains previous year. Last year 2024 this question has been asked. Why I am telling you the question of JEE mains? Because the question of JEE mains are repeated in NEET as it is, right? So it was also a controversial question. That is why I am telling you, right? It was a controversial question, right? So yes, so this thing in NET it is giving, they have given a different pattern, right? In NET, if you Google it, you will see a different electronegativity values here. But you should always consider NCERT, and that is your latest NCERT. So if in latest NCERT they have given that, firstly you will have carbon, then for silicon, germanium and tin it is almost similar, then you have to consider that it is almost similar, then it will increase to that 1 point. That means almost similar only, right? Okay, understood? So that becomes your electronegativity, right? Next is physical properties. So physical properties we have, physical properties, all group 14 elements are solids. Carbon, silicons are non-metal, germanium is a metalloid. Very, very important that germanium is a metalloid. That is why it is used in semiconductors. Whereas tin and lead are soft metals, right, with low melting points. Melting points and boiling points of group 14 are much higher than those of corresponding group number 13, right? Group number 14 will have more boiling point as compared to group number 13. As you can see here, here the melting points. There the first melting point was around, I think 1000 or 2000. Here it is 4373, right? For boiling point of carbon is not only there, right? We can't boil it, right? So silicon it is 3550. So definitely they are higher than the group number 13 elements, right? Okay. Okay guys, electrical resistivity they will not ask you. Now let us do the oxidation and trends in the chemical reactivity. So here we will talk about two oxidation states. First is +4 oxidation state, then you have +2. As I told you that lower oxidation state stability will increase down the group. So it is 𝐂𝐡𝐞𝐤 𝐿 So a very, very important question is asked from here. Very important question. Repeatedly it has been asked, right? Okay, repeatedly they have asked you question regarding out of lead and tin, which is a good oxidizing agent, reducing agent. That is from this paragraph, right? Okay. So now let us see that. So when you talk about this, lower oxidation state, that means +2 oxidation state is more stable down the group. So if you talk about PB, that is more stable in PB 2 positive as compared to 4 positive, because lower oxidation state is more stable down the group. If you talk about the higher oxidation state, considering about tin is more stable in +4 oxidation state as compared to +2 oxidation state. Is this thing clear to everybody? Why I am saying that? Lower oxidation state is more stable in heavier element, that means down the group, right? So this is what they have written here, that carbon also exhibit negative carbon will also, that we are not going to talk here. Since the sum of 4 oxidation state is very high, compounds in +4 oxidation state are generally covalent in nature, like carbon. I'm telling you that +4 oxidation state higher is more stable in the above elements, right, that are above in that group. So carbon is more stable in +4 oxidation state. That is why carbon exists as covalent. That is why carbon forms covalent compounds, right? So silicon also form covalent compounds, right? So in heavier elements, the tendency to show +4 oxidation state is increases in a sequence of this. That means carbon and silicon does not show any +2 oxidation state, but germanium, tin and lead, they can show +2 oxidation state, but that increases in this order. First for this, then for this. Lead has maximum tendency. It is due to inability of NS2 electrons. Why? Because when you go down the group, there are D and F electrons that are added here. Because of those bad friends, the outermost electron, right? This is the nucleus, this is the outermost electron. Firstly, you had no friends. You were like, I am not able to convince my parents. Then you thought, I will make some good friends. But your good friends are not your good friends, they are enemies. So what will happen? They will not only convince, they will not at all convince your parents, they will gossip about you with your parents, right? So these are the bad friends. So this is outermost electron, this is the nucleus. Because of those D and F electrons, which have very poor shielding effect, that electron will get attracted towards the nucleus, right? That is why that NS electron, this is your NS, this is your NP. For this NS electron, which is nearer to the electron, it is difficult to lose these two electrons. That is why only the outermost electron, that is p orbital, will be able to lose the electrons down the group. That is why +2 oxidation state is more stable down the group. Is that thing clear to everybody? Yes, Nandu is like, I want to sleep, ma'am. Okay. So now, the relative stability of these two oxidation states vary down the group. Carbon and silicon mostly exist as +4 state. Germanium forms stable compounds in +4 and only few compounds with +2 state because it is moderate. Tin compounds in both oxidation state +2. Now this is a very good, very important question. Tin forms compounds in both oxidation states, but tin in +2 oxidation state is a reducing agent. Can you tell me why? They are saying that tin in +2 oxidation state is a good reducing agent. Can you tell me why? What is a reducing agent? It wants to reduce the other person and itself wants to get oxidized. It itself wants to increase the oxidation number. Definitely, it wants to increase the oxidation number from +2 to +4. Only then itself it will get oxidized, because itself it is getting oxidized. That is why it is acting as a good reducing agent. And this is a very, very asked question to you. It has been asked so many times in your exams. You can see that, right? And in +2 oxidation state is a reducing agent. Lead, very, very important line. They are saying lead in +2 oxidation state are stable, and in +4 oxidation state it is a strong oxidizing agent. Very, very important question, right? Very, very important question, that we know that lead is existing in +2 and +4, right? So lead, when it is in +4 oxidation state, it is a good oxidizing agent. Why? Because it wants to oxidize someone else and itself wants to get reduced, right? Itself want to get reduced means it wants to decrease the oxidation number. That means from +4 to +2, definitely it wants to decrease the oxidation number, because in +2 it is more stable, right? Okay, got it. Now, yes, easily oxidized. Now this, from this assertion reasoning question can be asked, which of the following is correct answer can be asked, right? So these kind of question can be asked from here. In tetravalent state, the number of electrons around the central atom in a molecule is 8. Now they are saying that it has full complete octet, so it is not acting as any Lewis acid or basis. Being electron precise molecules, they are normally not expected to act as electron donor or acceptor species. Just like boron was acting, because in boron, BF3, right, we talked about BF3, we talked about AlCl3, they had 6 electrons. So AlCl3 and other elements tend to form dimer, but BF3 was acting as a Lewis acid, right? But here it is not the case, right? Although carbon cannot exceed its covalency more than 4, other element. Just like boron, the first element will not have the vacant d orbitals. That is why the first element, just like boron was not able to expand its covalency beyond 4, same as carbon will not be able to do the same, right? Now, it is because of presence of d orbitals in them. Due to this, their halides undergo hydrolysis and have tendency to form complexes by accepting electron pair from donor species. This is what they are saying. They are saying except for carbon, like if you talk about silicon halide, germanium halide, tin halide, they will undergo hydrolysis, right? For example, the species like these exist where the hybridization of the central atom is sp3d2. Very, very important. Hybridization, they can easily ask you that what is the hybridization of these species, right? For carbon, it cannot expand its covalency. They can expand the covalency, right? Okay, that is why it is 6 here, 6 here, 6 here. Because silicon, germanium, tin, they can expand the covalency. Next is reactivity towards oxygen. If you talk about oxygen, all members when heated in oxygen form oxides, definitely. If you talk about the reactivity, we know that it is +4. Generally, it is existing like that. Cross valency, it will be M2O4. Cancel it out, it will be MO2. This is the oxide that is formed. Now, talking about the oxides, right, very, very famous. So, they are saying that two kind of oxides are formed. One is MO, other is MO2, right? Okay, one is MO, other is MO2. So, when it is existing as +4, it is forming MO2 oxides. For example, it is existing as M2 positive, then O2 negative, then it will form MO. If it is existing as M4 and 2 negative, then it will form MO2. So, two oxides are formed here. Two oxides are formed here. We know that carbon monoxide, carbon dioxide. Similarly, okay. So, silicon oxide only exists at higher temperature. Oxides in higher oxidation states are generally more acidic than lower oxidation states, right? That means here it is more oxidation state. Metal is in more oxidation state. So, it is more acidic as compared to lower oxidation state. The dioxides are acidic. Very, very important it is, right? That the dioxides are acidic in nature as compared to monooxides. Whereas now, very important thing, that if you talk about tin and lead, they are amphoteric. Now, if you talk about dioxides only, because they are existing in higher oxidation states, so they are definitely more acidic. And now we are doing the variation of these oxides down the group, right? We know that metallic character is decreasing, right? Sorry, non-metallic character is decreasing. That is why acidic character is also decreasing. That is the reason carbon monoxide, silicon and germanium, they are acidic, but tin and lead dioxides are amphoteric in nature. Now, if you very, very important, this is carbon monoxide is neutral in nature, right? Then germanium oxide is distinctly acidic, whereas tin and lead oxides are amphoteric in nature. From here also the question are asked. Very important. Question like match the following, which of the following is acidic, which of the following is neutral oxide. These kind of questions can be asked, right? Okay. Yes, you will also get oxidized if there is someone to oxidize you. If someone is there to reduce you, then you will get reduced. Okay. Now, but I think oxidation is better, right? Now, reactivity towards water. Now, reaction is not very important. Carbon, silicon, germanium are not affected by water, right? If you add water into it, this is tin, right? Now, carbon, silicon, germanium have no reaction with the water, but tin has the reaction. Now, very important line here. Tin decomposes steam to form dioxide and dihydrogen gas, right? Tin will need still temperature with water. But if you talk about lead is unaffected by water. Probably, now here we have a different reason, right? The reason is because of the protective oxide film formation, right? So, from here, reactions are not important for you. Again, I am saying that. What is important for you to understand that? They can ask you, out of the following, which dioxide does not react with water? So all the dioxides will not react except for tin, right? Tin will only react with water, and that too with steam to form dioxide. Others will not, right? Okay. So theory is more important basically in this chapter, right? Then we have reactivity towards halogen. Again, the same thing. Now these form MX2, MX4 kind of dihalides, right? Why they form like this? So basically because we have M2 positive, X negative, so it will be MX2. If we have M4 positive and X negative, it will be MX4, right? So these are the two oxides that can be formed here. So except carbon, all other members react directly with halogen under suitable condition, right? But to make the halides, most of MX4 are covalent in nature, right? Covalent in nature. The central metal atom of these halides undergo sp3. Now, why we are saying sp3? If we talk about MX4, it is existing, it is having 4 sigma bonds. That is why it is sp3 hybridized, right? Then also, this also you don't need to remember. Exceptions you need to remember, right? Now, exceptions are tin fluoride, lead fluoride, which are ionic in nature. Now, mark this important. I think this is also your previous year question of NEET. This also question I have seen. So this is also your previous year question of NEET directly. See, whenever you see exception, you just underline that because that directly will be, as it is, will be asked to you in the exam, right? So directly the exceptions are asked in NEET exam, right? From inorganic chemistry, focus on the exceptions, not only the trends, exceptions like these also, right? So exception, they're saying all the other halides will be covalent except for tin fluoride and lead fluoride. They are ionic in nature. Now next is very important, this question has also been asked, that lead iodide does not exist, right? I think assertion reasoning question has been asked from this one, right? This is the question. First statement is lead iodide does not exist, right? Lead tetraiodide does not exist. Reason is because PBI bond initially formed during the reaction does not release enough energy to unpaired 6s2 electrons and excite one of them to higher orbital to have 4 unpaired electrons around the lead atom. So basically what they are saying that one by one the bond will be formed, right? You have 4 bonds of PBI, right? So when one bond we are forming, outermost is what? You have 6s2, 6p2, right? So basically you will have these 4 electrons, right? You will have these 4 electrons, right? Now wait a minute, sp3, yes. So you will have these 4 electrons, right? So they will together combine to form a sp3 hybridized orbital, right? You will have 1, 2, 3, 4. This is what you are thinking, that it should form a sigma, 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 right? But actually in the case of PBI, this does not happen. Why? Because they are saying when you have 6s2, 6p2, when one bond from this one electron, right, we are forming one bond, that is PBI. After that, what was supposed to happen? This should also give us some electrons to pair up with the other iodine, right, so that they can form a sigma bond. Now what is happening? During the reaction, the PP bond initially formed during the reaction does not release enough energy to unpair the 6s2 electrons that are present here. If we unpair this, only then they will also form sigma bond with the other iodides, right? We need to, this is 6s2, basically it's like this, right? It's like this. So we need to give it energy to unpair these 2 electrons. But that much energy is not released in the formation of PBI. So from where? From outside it will get the energy? No, right? So that is why the electrons and excite them to higher orbital to have 4 unpaired electrons and around the lead atom. That does not happen, right? Okay, that means this sp3 hybridized orbital is not formed only, right? That is the reason this PbI4 does not exist. A very, very, very important thing. Okay, understood? Yes, guys, everybody in the chat box. Electrons around the lead atom. Heavier members from GE, germanium to lead, are able to make halides of formula. Now, why heavier elements are able to make this formula? Because heavier elements will exist in M2 positive. That is the reason. Stability of dihalides increases down the group because M2 positive stability increases down the group. Considering the thermal and chemical stability, GeX4, germanium halide, is more stable than germanium dihalide. Can you tell me why? Because germanium 4 positive is more stable as compared to germanium 2 positive. But Pb2 positive is more stable as compared to Pb4 positive. That is why PbX2 is more stable as compared to PbX4, right? Except CCl4, other tetrachlorides are easily hydrolyzed, right? If we talk about other tetrachlorides, right, for silicon, germanium, they are easily hydrolyzed except for carbon, just like in the case of boron. For boron also we did the same thing. Do you remember that? For boron, what we did? That boron has an anomalous behavior, right? Boron will behave very differently as compared to the other elements. This we did in group number 13. Same is the case with group number 14, right? Same thing will happen here. First element, because of the vacant, it does not have any vacant d orbitals, it will not be able to get hydrolyzed, right? Okay, same thing, same reason. Are easily hydrolyzed by water because the central atom can accommodate lone pair of electrons from oxygen or water molecule in the vacant d orbital. Same thing, right? Hydrolysis can be understood by taking the example of SiCl4, because carbon tetrachloride does not show any hydrolysis. This will show hydrolysis. It undergoes hydrolysis by initially accepting lone pair of electrons from water, right, into the d orbital because it has vacant d orbitals, finally leading to the formation of very important compound, that is silicon hydroxide, right? So this reaction is important and a very simple reaction. You have lone pair, this is silicon, it will attack here. You will firstly, it will replace 1 Cl, then 2 Cl, then 3, then 4th, right? And hence you will have the formation of salicylic acid, right? Okay, important thing it is. Next is important trends and anomalous behavior of carbon. This is same as boron. Same things you will see are being repeated here. In the first member of other, carbon also differs in the rest of the member. It is due to same thing. Smaller size, higher electron negativity, always. These three reasons always you will see in all the groups, right? Smaller size of the first element, higher electron negativity, higher ionization enthalpy because of the smaller size, very difficult to lose the electron. Then this is the most important reason, unavailability of d orbitals, right? Because of this unavailability, it is very difficult to accept extra electrons into any vacant thing because it has no vacant d orbitals. That is why it cannot expand the covalency. That is why it is not hydrolyzed. In carbon, only s and p orbitals are available for bonding. Therefore, it can only accommodate 4 pairs of electrons. This would limit the maximum covalency to 4, right? Okay, and they cannot expand the covalency beyond 4, right? Now, next thing is the multiple bonds. What kind of multiple bonds carbon can form? We know that carbon can form double bond, triple bond. How it can form, right? So let us see that. Carbon also has unique ability to form p-pi multiple bonds, right? It can form p-pi multiple bonds. That is why you have alkanes, you have alkenes, alkynes with itself and with other atoms of the smaller size, smaller size and high electronegativity. We know that carbon can form double bond with oxygen, triple bond with nitrogen. They are highly electronegative as compared to this. The size is not very large. right? They are the uppermost element of their group. That means their oxygen is also smaller in size as compared to the other group elements. Nitrogen is also smaller in size as compared to the other group elements, because down the group the size will increase. So oxygen and nitrogen are the first element, so they are definitely smaller in size. It can also form double bond with itself, triple bond with itself, right? So it has the ability to form multiple bonds. For example, multiple bonds these exist. Heavier elements don't form p-pi bonds. Reason is because of their size. Because of their atomic orbitals are too large and diffuse to have effective overlapping. Now see one thing, that multiple bonds are formed by sideways overlapping. This is one orbital, this is one orbital. They will overlap like this, right? And sigma bond is formed by head-on overlapping, right? So that is the reason, because down the group, the orbitals, the number of principal quantum number will increase, the shell number will increase. That is the reason the size of the shell will increase, right? That is the reason the overlapping is very difficult. Sideways overlapping is difficult. Okay? Okay, guys, understood this? Now, carbon atoms have tendency to link with one another through covalent bonds to form chain and rings. We have also seen the cyclic compounds, aromatic compounds, right? We have seen so many compounds of carbon. This property is called catenation, right? That is self-linking property. That is why, because of this catenation only, it has diamond structure, which is highly network structure, because carbon is forming bonds with carbon only. That is why we have a large number of organic compounds, and we have very large organic compounds, right? It has 620, 6,006, I am saying, C60, C80, C90. Why? Because of catenation. Down the group, the size increases and electronegativity decreases, and thereby tendency to show catenation also decreases. So silicon also show catenation, but very less catenation it will show. This be clearly seen in bond enthalpies, the order of the catenation in carbon maximum, then silicon, then it will decrease only. Eventually it will go zero, right? Lead does not show any catenation, right? Okay, so now this is the bond enthalpy. Carbon, it has a maximum energy, right? Then it is decreasing down the group. Why? Because size is increasing, right? If size is smaller, the bond will be stronger. If size is increased, the bond length will increase, and hence the bond dissociation enthalpy will decrease, right? Okay. Due to the property of catenation and p-pi bond formation, carbon is able to show allotropic forms. Now they are saying carbon shows allotropic forms. Graphite, diamond, Buckminster fullerene, these are the allotropic forms of carbon, right? So carbon exists in different things. So first is diamond and graphite, which are well-known crystalline forms of carbon. Then it exists as fullerenes, and we have C60 fullerene only in our syllabus, but there are other fullerenes also. Discovered by Croto, and this you don't have to learn. For this discovery, they were awarded a Nobel Prize. Now let us see what is diamond. Okay. So diamond is, it has crystalline lattice, right? Diamond network-like structure, right? So firstly, I'll just show you the structure here. Then we will see the theory part, right? So now structure is very simple. It has a network-like structure. Every single carbon is forming 4 bonds. That is why all the bonds are tetrahedral in nature. If you talk about anything here, if you talk about the example of this particular, if you take the example of this particular carbon here, this carbon is making 1, 2, 3, 4 sigma bonds. That is why it is sp3 hybridized, and that is in the form of tetrahedral. It is in the form of tetrahedral only, right? So all are tetrahedral only, right? A network complex structure is formed. That is why diamond is the hardest material, because a very strong network is formed between these carbon due to the property of catenation, right? Okay, understood? Yes. Which doubt you have? Tell me. Now, which doubt you have? Hanji Nandu. I thought Nandu has gone to sleeping. He was like, okay, ma'am, I am tired. I want to sleep, ma'am. Carbon number of bonds, can you tell me why? Because of its property of catenation, it is tetrahedral, right? So that is why it is observed that it can form bonds with itself only, right? To complete the tetravalency, right? Okay. Now diamond has a crystalline lattice. Each is having sp3 hybridization linked to 4 other carbons. This also we have done. The carbon-carbon bond length is 154 picometer. Structure extends in space and produces a rigid 3-dimensional structure, network-like structure. That is why this is the hardest material. And directional covalent bonds are present throughout the lattice. It is very difficult to break the extended covalent bonding. That is why diamond is hardest substance. It is known as abrasive for sharpening hard tools, right? The diamonds that are not useful for us, they are not very good reflecting diamonds we are talking about here. In making dyes in the manufacture of tungsten filaments for the electrical light bulb, right? The diamonds that are not very reflective, that diamond they are talking about, right? The diamond that is very good reflector of light, that we used in jewelry, right? Okay, so they're also used in dentistry, also they are used, right? Next is graphite. Now graphite is basically very soft. See, same but different. Why? Because diamond and graphite both are made from carbon only, but the properties are entirely different. Diamond is the hardest material, and graphite is there in the lid of the pen, right? That pen, that is black thing in your pencil, that is graphite. Okay, that is very soft, right? We can easily break it, right? So if you talk about the graphite here, so graphite is basically looks like this. Graphite has a layered structure, right? So basically in different, this is for example the first layer, this is the second layer, this is the third layer. Different layers are attracted to each other by the van der Waals forces. Here we have these dots are the van der Waals forces. But if you zoom it in one layer, that has very important thing, that has hexagonal rings. Okay, so hexagonal rings means this thing, 1 2 3 4 5 6, that means one hexagonal rings are all around that one layer. So now what you observe, if you pick out one carbon from here, if I pick out this carbon, it is attached to 1 2 3 bonds. So that means 3 sigma bonds it has. That is why that layer of graphite that is having sp2 hybridization, and can you tell me sp2 hybridization is trigonal planar. It is trigonal planar. That is the reason graphite is in one layer, is in one plane, because the hexagon are in one plane, right? Second thing is, if you have observed that in electrochemistry, we use graphite electrodes. We don't use diamond electrodes, right? So basically graphite is a very good conductor of electricity, because graphite, it is only having 3 bonds, but in carbon we know that it has 4 bonds. That means one electron is like not in the bonded state. That means every single carbon has 1 electrons that are free, right? So there are so many free electrons, that is why it is a very good conductor of electricity, right? Okay, now let us see what they have written in the theory, right? So graphite has layered structure. Layers are held by van der Waals forces, that are weak forces, and distance between two layers is 340 picometer. Each layer is composed of planar hexagonal, as I told you. Why planar? Because of sp2 structure, hexagonal rings, right, which is having 141.5 picometer. Each carbon atom is sp2 hybridization, right? 3 sigma bonds, because it is forming 4th electron forms a pi bond, right? Because 2 electrons are free, right? Their electron crowd will overlap with each other, right? And they will form a pi bond, which is not a very stable bond, right? Which is not at all a strong bond. That is why they are also in the free state, right? So the electrons are delocalized over the whole sheet. Electrons are mobile, right? The electrons are moving, they are delocalized here, right? It's like this. This also has one electron, this also has one electron, this also has one electron. Sometimes this electron will overlap with this one, sometimes it will overlap with this one. Sometimes it will form a pi bond here, sometimes it will form a pi bond here. That means the electrons are in the delocalized state, right? Okay, the electrons are in the delocalized state. Okay guys, okay, pencil pencil, मेरी क्लास नहीं कैंसिल, so sorry about it. Therefore, graphite conducts electricity along the sheet, right? It's a very good conductor. Graphite cleaves easily between the layers because van der Waals forces are very easy to break. It is very soft and slippery. Have you seen that pencil? It's very soft and slippery, right? For this reason, graphite is used as dry lubricant in machines running at high temperature, where oil cannot be used as the lubricant. Where you can't use oil as a lubricant in some machines, you will use graphite as a lubricant. Okay? Yes, 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 yes. Now, let's talk about fullerene. So, fullerene is basically, you have C60 in your syllabus, right? Fullerene has a football-like structure, as you can see here. It has a football-like structure. It will have pentagonal rings. Wait, let me show you. It will have pentagonal rings like this, right? It will also have hexagonal. This is a pentagonal ring, and it will also have hexagonal rings like this, right? It will also have hexagonal. If you ever see football, right, it has white and black patterns, right? Black is usually pentagonal, and I think white is hexagonal, right? I need to observe that, but yes, it also has two different rings, right? It also has two different rings, pentagonal and hexagonal rings, right? So let us see what kind of question they can ask you from the theory. First is that fullerenes are made by heating of graphite in an electric arc in a presence of inert gas such as helium and argon. So it is prepared from graphite. That is the first important part. Made by heating of graphite, right? The sooty smell formed by condensation of vaporized C11 small molecule consists of 660 with smaller quantity of 670 and traces of fullerene consisting of even the number of carbon atoms up to 350 and above. But you have C60 only in your syllabus, right? Mainly C60. Fullerene are the only pure form of carbon, right? Basically, the byproducts are also formed. In this, you have C70 also, but we will talk about in detail about C60 only. Fullerene are the only pure form of carbon because they have smooth structure without having dangling bonds, right? They have very smooth structure. There is no dangling bond in between. Fullerenes are cage-like, right? Cage, you can see it's like a cage only. It's like a football only. Molecules have shape like saucer ball or football, and that is why it is called Buckminster fullerene, right? It was also similar to a building that the scientists observed back then. That is why he named it as Buckminster fullerene, right? It consists 20. This is important. This is the question that they can ask you, that how many 6-membered rings? So basically 6 and 5. One answer is 20, other answer is 12. Now we know that 12 is in the table of 6. So that is why you will write the opposite here, 12. And 5 is in the table of 20. That is why you will write 20 here. Basically opposite you have. This is just a way of remembering here, right? Just a way to remember this, right? No logic here, right? Because here the students get confused that which has how many rings, right? So 20 you have 6-membered rings and 12 you have 5-membered rings. The 6-membered rings is fused with 6 or 5-membered rings, but a 5-membered ring can only fuse with 6-membered rings. So very, very important point, right? if you talk about this is your 5-membered ring, right? This is 5-membered ring. Now this will only fuse with the 6-membered ring. How? This is one 6-membered, then this is another 6-membered, this is another 6-membered, right? This is another 6-membered, right? This is another 6-membered. This is a very, very important point, right? But the 6-membered ring can also fuse with 5-membered or 6-membered, but 5-membered ring will always fuse with the 6-membered ring only, right? Okay, very, very important point. Next, we have all the carbon atoms are equal and they undergo sp2 hybridization. How come they undergo sp2 hybridization? Pick out any carbon here. This is the carbon that you want to pick. Let's pick this carbon, right? It is having 1 bond, 2 bond, 3 bond, 1, 2, 3 sigma. That is sp2 hybridized only, right? So all the carbons have sp2 hybridization, right? Each carbon atom forms 3 sigma bonds. That is the reason. The remaining electron at each carbon is delocalized, just like the graphite. Molecular orbitals, right? Which in turn give aromatic character to the molecule, right? Because of these cyclic rings here having delocalization, cyclic, complete conjugation it has. That is why it is a aromatic structure, right? This ball-shaped molecule, this question also I have seen, I think in some practice book, very important. 60 vertices, this one, that Buckminster fullerene is aromatic in nature, right? The ball-shaped molecule has 60 vertices, that means 60 carbons it has, each one occupied by one carbon. It also contains both single and double bonds, right? It will have because of the delocalization. Spherical fullerene are also called bulky balls in short, right? Okay. It's like a ball only, na? You can see it's like a ball only. It's very important to know that graphite is thermodynamically more stable allotrope of carbon. Therefore, diamond is not, if you talk about, they're saying that the graphite is thermodynamically more stable allotrope of carbon. Therefore, graphite is taken as 0, right? This, we have used this in thermochemistry, right? This particular statement is used in thermochemistry, right? That which allotrope is more stable? Graphite is more stable. That is why the delta H of graphite is taken as 0, delta H formation. We think that in reality, like in phosphorus also we observe that which is the elementary state of this thing. Similarly, carbon has the elementary state as graphite, right? This is a very important point that I have discussed in thermochemistry, right? That is why the delta H formation is taken at 0. Delta H formation value for diamond and fullerenes are 1.9 and 38.1, right? Because Buckminster fullerene is definitely prepared from graphite, right? But diamond has 1.9, right? Okay, so it's a very important thing that in which is the standard state of carbon, that is graphite. Okay, you can write it here. Standard state of carbon is graphite. Very, very important question. Okay. Other forms of elemental carbon like carbon black, coke, charcoal are all impure forms. It has some impurities in it, like charcoal. You must have seen that the people who do iron by that using that charcoal, right? Actually, it is not a pure form of carbon, right? So pure form is very soft. So carbon black is obtained by burning hydrocarbons in a limited supply of air, right? Charcoal and coke these are basically the fuels, are obtained by heating wood or coal respectively at high temperature in the absence of air, right? So carbon black is formed by presence and charcoal and coke is formed by absence of air, right? Now you have some uses of carbon, right? Graphite fibers embedded in plastic materials at high tensile strength, lightweight composites. The composites are used in products such as tennis rackets, fishing rods, aircrafts, canoes. Then you have being good conductor. Graphite is used for electrode. This is important for you in batteries and industries. In electrolysis, right? This is important for you to know, right? Then we have crucibles made from graphite are inert to dilute acids and alkalis, right? Then we have being highly porous, activated. Now this is important. Activated charcoal, right? This is used as a catalyst, okay? Is used in absorbing poisonous gases. Activated charcoal has pores in it. That is why to observe the toxic gases, activated charcoal is used. This is also a very important point, right? This is also important point for you. Question can be asked. Also used in water filters to remove organic contaminators, and in air conditioner system to control the odor. This is activated charcoal can be used. Carbon black is used as black pigment in black ink and as a filler in automobile tires, right? Then coke is used as fuel and largely as reducing agents in metallurgy. Then diamond is precious stone and used in jewelry. It is made in carats, right? Okay. So, some of the important points related, some of the important compounds of carbon and silicons. Okay, guys, let us see. Okay. Okay, guys, everybody in the chat box. Everybody in the chat box. Everybody in the chat box. Okay. Okay. Now, some important compounds of carbon and silicons. Let us see. Oxides of carbon. So, first is oxides of carbon. Carbon monoxide, carbon dioxide. Carbon monoxide, firstly, how it is prepared. With carbon and oxygen at a limited supply of oxygen, carbon monoxide is prepared. Right, this is usually like it is very, very dangerous for our body. On small scale, pure CO is prepared by dehydration of formic acid. If you want this question, we have also done in organic chemistry, that when you heat formic acid, then you will have the formation of carbon monoxide and H2, and that is why this becomes the important reaction. That on heating formic acid, you will get carbon monoxide, right? Okay. Then on commercial scale, it is prepared by passage of steam over hot coke, right? This is steam, that is over hot coke. Then we will have the formation of CO and H2. And CO and H2, now this is very, very important, right? That CO, carbon monoxide, along with hydrogen gas is called water gas. But carbon monoxide along with nitrogen gas is called producer gas. This is very, very important, right? When air is used instead of steam, if you use air here, so if you use direct steam, that is water and heat, then you will get water gas. If you use oxygen and nitrogen that is present in the air, then what you will, because in the air, the maximum amount, the maximum abundance is of oxygen and nitrogen, then you will get the formation of producer gas, that is carbon monoxide and nitrogen, right? Okay. Okay, guys. Next is water gas and producer gas are very important industrial fuels. Carbon monoxide and water gas or producer gas can undergo further combustion, forming carbon dioxide on the liberation of heat. Right? Carbon monoxide is colorless, odorless, and almost water insoluble gas. Very toxic. Reducing agent, reduces almost all metal oxides other than those of alkali and alkaline earth metals. Aluminium and a few transition metals. This property of carbon monoxide is used in extraction of metals from their oxide ores. So, for example, this is oxide ores. So, on treating with carbon monoxide, it will take out the oxygen. It will act as a reducing agent here, right? That is why to purify other oxides other than alkali and alkaline earth metals and some of the transition metals, alkaline earth metal, aluminium and few transition metals, it can act as reducing agent for rest of them. In now this is a very important paragraph. This full paragraph is important. From here also, easy it is, but it is important, right? Carbon monoxide molecule, there are 1 sigma, 2 pi bonds. Have we done this in chemical bonding or not? In detail, we have done the structure of, with the Lewis bond theory, we have done this Lewis dot structure, we have done the structure of carbon monoxide, right? We have done that in detail, right? It will have 2 pi bonds between carbon and oxygen, because this is the structure, because of the presence of lone pair on carbon, carbon monoxide molecule act as a donor and react with certain metals when heated to form metal carbonyls. Have we studied about metal carbonyls? Have we studied about metal carbonyls? That is why this whole paragraph is important, right? Carbon monoxide, the structure we have done in chemical bonding. Metal carbonyls, the different structures, this also, the back bonding, synergic bonding, right? This also we have done, right? Okay, that is why this is important. This metal carbonyls, their synergic bonding or back bonding, that is also very important, right? The highly poisonous nature of CO arises because of its ability to form complex with hemoglobin. So our hemoglobin has the affinity with oxygen. It loves oxygen. So when we inhale, now what is happening? Inside my body, right, oxygen carriers, this hemoglobin will carry that oxygen, right, and bond it, right, and hence it will carry that blood from that hemoglobin. Basically, that hemoglobin will carry that oxygen throughout our body, right? Now, for example, sometimes what happens now, oxygen is a loyal friend, right? Now, for example, you have a very unloyal, very double-faced person, that is carbon monoxide. But we know that emotionally what kind of human beings we are. We are more attracted towards toxic people, isn't it? Do you agree with me or not? Aren't we more attracted towards toxic people in our life, right? So there will be a good person, there will be a bad person. We'll say, oh, good person is so direct, so bold, oh my God, I don't want to hear anything. Oh, this person is so sweet. What if they have double face? What if they are behind my back, they are something else? We'll be like, okay, you are a good person. We'll choose the toxic person, right? Isn't it? I am to like that, yeah. What to do, right? I think I need to now it's still better, but when I was of your age, I was definitely like this. Now, hemoglobin, when it sees carbon monoxide, it's like, oh my God, carbon monoxide I have, right? She'll be like, okay, I have more love for carbon monoxide, right? But actually, carbon monoxide is dangerous for the body. It can even lead to death, right? That is why 𝐂𝐡𝐞𝐤, right? If you know what is 𝐂𝐡𝐞𝐤, right? Basically, when you burn coal with heat in limited supply, carbon monoxide is produced, right? So what happens if some cases have been observed that in some villages, right, in cold, in winters, they had 𝐂𝐡𝐞 on in their houses. And what happened? Because of that carbon monoxide that was produced in a closed room, that lead to death of the people, right? Okay, so yes. Now, which is about 300 times more stable than oxygen hemoglobin complex, right? This prevents hemoglobin in the red blood corpuscles. What is this pronounced as? Corpuscles. You are bio background, so you know better what is this pronounced as. That is why I too hate bio. Reason being, I hate the words. Pronunciation is more difficult, right? From carrying oxygen around the body and ultimately resulting to death, right? That is why carbon monoxide is that much harmful. So now let us talk about carbon dioxide. Very, very not harmful at all. It's prepared by complete combustion, right? We will have the formation of carbon monoxide, or with methane we can have the formation of carbon monoxide. Commercially, it is prepared by calcium carbonate with HCl, right? Now, calcium carbonate with HCl, it will form calcium chloride plus CO2 plus water. Because bicarbonates or carbonates with acid, they forms salt, then carbon dioxide, then water, right? Then we have on commercial scale, it is obtained by heating limestone. It is colorless, odorless. Its low solubility in water makes it of immense biochemical and geochemical importance. With water, it forms carbonic acid, right? When it is reacted with water, it is forming carbonic acid, that is H3CO3, which is a weak dibasic, right, acid. And after that, dissociate into two steps. So if you dissociate, it will dissociate into HCO3 negative. Then it will form a carbonate ion, bicarbonate and carbonate ion. Now, this buffer system helps to maintain pH of the blood between 7.26 and 7.42, right? So this is a question that they can ask you, that in our body, right, that carbonic acid, when it is dissociated to HCO3 negative, these two things, we know that our blood is a buffer. That means it will, even if you add acid into it to that limited amount, right, then it will not change its pH. The reason is the stability because of H2CO3 and HCO3 negative, right? Being acidic in nature, it combines with alkanes to form metal carbonates. Carbon dioxide, which is normally present only very less, that is 0.03 in our nature, right, atmosphere, is removed from it by the process known as photosynthesis. We know that plants, they catch carbon dioxide and give us oxygen. That is why it is very important to have greenery around you, right? This the process you already know. In lower classes, we have studied this. We had sunlight, chlorophyll, that carbon dioxide is converted to oxygen. It produces energy here, right? Okay, in the form of glucose. By this process, plants make food for themselves as well as for animals and human beings that we eat. Unlike carbon monoxide, it is not at all poisonous, but the increase in combustion of fossil fuels and decomposition of limestone for cement manufacture is recent years seem to increase the CO2 content in the atmosphere. Now, it's not poisonous, but you can't have that much carbon dioxide in the air because of the increasing vehicles and all of these things. We use ACs, refrigerators, all of these things produces carbon dioxide, and because of that, there's increased CFCs also. And one reason is increased amount of carbon dioxide. There is greenhouse effect, that is global warming that we have seen. Raise the temperature of the atmosphere, which might have serious consequences. But now, right, definitely work is going on this. Carbon dioxide can be obtained as solid in the form of dry ice. This though, guys, whenever you go to any concert or even in weddings nowadays, right, there is that with that matkas, right? So I have gone to a wedding recently. So there was this matka all over in the entry when the bride was entering, right? The bride was coming from there, and all over I could see dry ice, right? So dry ice all over the floor, right? So that is basically your dry ice, which you call, oh my god, ma'am, this is such a interesting thing, ma'am. That is nothing but that is dry ice only, right? Dry ice is used as refrigerant for ice creams, frozen foods, right? It is used. Gaseous carbon dioxide is extensively used in carbonated soft drinks. This also we have studied in solution chapters, that carbon dioxide is at a high pressure. It is there in the soft drinks, right? Carbonated drinks. Being heavy and non-supporter of combustion, it is used as fire extinguisher. Very, very important that it is also, because it is oxygen in the air, right? That basically, when we call fire extinguishing industry, what they do in that, the reaction happens in such a way that carbon dioxide is ejected into the atmosphere so that the content of oxygen can decrease, because oxygen is highly flammable, but carbon dioxide is not flammable, right? So a substantial amount of CO2 is used to manufacture urea, right? To manufacture urea also, this is used, right? So now we are seeing the resonating structure. Molecule carbon undergoes sp hybridization. How come? Because this is sigma, this is sigma. Two sigma bonds, it is sp hybridization, right? Two sp hybridized orbitals overlap with two p orbitals to form two sigma bonds, while other will form p pi bonding. This we have seen in chemical bonding. While oxygen atom, this results in linear shape. Have we done this structure in detail or not? Everybody in the chat box tell me. Have we done chemical bonding in detail or not? Have we done that or not? Everybody in the chat box, and let's complete the target. Let's complete the target of today's likes by 100 at least, right? Okay, that's why I think you can do that in within 5 minutes, right? So this though we have already done, and so many times we have done, right? So this results in linear shape and with no dipole moment. Why? Because it also cancel out, so there is no dipole moment. Those students who are not able to understand this thing, watch chemical bonding by Diksha ma'am. You will be able to understand that, right? Okay. Next is silicon dioxides, right? Let us talk about silicon dioxides now. Let us talk about silicon compounds. That is going to be the last thing for today's class. Silicon compounds also, you don't have to do everything here, right? There are some things that you can skip. There are some reactions that you don't need to do. Some structures that you should definitely do, right? So some of the, this is same as what we did in boron compounds, right? So silicon dioxide, 95% of the earth crust is made up of silica and silicates, right? It is a very, very abundant element. Silicon dioxide, commonly known as silica, occurs in several crystallographic forms. First, very important is quartz, crystobelite, then tridymite are some of the crystalline form of silica. Quartz is normally used, right? Then they are interconvertible at suitable temperatures. Silicon dioxide is covalent, three-dimensional network solid, which each silicon atom is covalently bonded to tetrahedral manner to other four. So basically this is what they are talking about, right? This is what they are talking about, that each silicon is bonded to, for example, this silicon is bonded to 1, 2, 3, 4. 4 other atoms, tetrahedrally it is bonded. sp3 hybridization silicon has. And it is forming a network-like structure here. Now let us see the theory part. Each oxygen in turn covalently bonded to another silicon atom as shown in figure. Each oxygen is bonded to silicon. Each oxygen is bonded to 2 silicon atoms, right? Each corner shared with another tetrahedron, right? Each corner is shared with another tetrahedron. The entire crystal may be considered as giant molecule, right, which is having 8-membered rings are formed with alternate silicon and oxygen atoms. Now, how come? Acha, tell me, 8-membered ring also we have seen somewhere else also. In boron compound also we saw 8-membered rings, right? In boron also we saw 8-membered ring that I have mentioned in the structure only. Right, here also, how come 8-membered? 1, 2, 3, 4, 5, 6, 7, 8. So it is again 8-membered ring. You can write it here. 8-membered ring. Very, very important it is. From silica also the questions are asked in your syllabus. Okay. From silica also, even if it is not mentioned, they will not mention in your syllabus that do silica. You say, ma'am, I will skip silica. Even from silica the questions are asked. Right. That is why specially I am doing this. Right, so are formed with alternate single and double bonds. Okay, now we have silica in its normal form is almost non-reactive because of very high SiO bond enthalpy. It is very difficult to break, right? It resists the attack by halogen, dihydrogen, most of the acids and metals even at elevated temperature. However, it is attacked by very, very important HF and NaOH. Very, very important. Right? It will only get attacked by HF and NaOH. Right? You just need to remember it is attacked by NaOH and HF. Quartz is extensively used as a piezoelectric material. It is made possible to develop extremely accurate clocks, modern radios, television broadcasting, and mobile radio communicators, right? Then silica gel is used in drying agent and as a support for chromatographic materials. And chromatography, we have seen silica gel there, right? Do you remember in qualitative quantitative analysis we have done this, right? So then we have 𝐂𝐤 an amorphous form of silica is used in filtration process. Just need to remember the name here, that is 𝐂𝐤, right? An amorphous form of silica, right? Just remember the name. Next is silicons. Now silicons, you have to remember the units here, right? So basically group of organosilicon polymers which having, this is the repeating unit. This question can be asked to you, that what is the repeating unit in silicons, right? The starting material for manufacture of this is alkyl, is substituted, this you don't have to remember, right? Then you have when methyl chloride react with silicon present on this, form this. Don't remember the reactions, right? Okay, just go through this once, that okay, when alkyl chloride is reacted with silicon, it forms this kind of compound. Then after further hydrolysis, it is forming this silicons. In silicons, what you have, right? In silicons, hydrolysis of dimethyl, this followed by condensation, polymerization yields straight chain polymers. Now from here also you will have silicon, this is CH3, OH, OH, CH3. After this there will be condensation, right? That means water will be eliminated. Then you will have the formation of this silicon, right? This is the silicon. It is a polymer. The regular unit is this one. This is the unit, R2SiO. 2 alkyl groups, 2 silicon, 2 alkyl groups, 2 silicon, right? And 1 oxygen, right? And this is n times repeated. That is called silicon, right? Just remember the repeating unit here. The chain, right? The chain length of the polymer can be controlled by adding CH3 thrice SiCl to control where you want to stop the chain thing, right? Which block this chain, right? Okay. And this is, for example, it is going and going. So to block this thing here, you react with CH3 thrice SiCl and then you will have the formation of CH3 here and hence the chain will stop here and this is called the silicon with n number of units here, right? Repeating units here. Then silicon being surrounded by non-polar alkyl groups are weaker repelling in nature, right? Because it has CH3, CH3 which are hydrophobic in nature, right? So they have in general high thermal stability, right? The bond are very difficult to break with heat, high dielectric strength and resistant to oxidation and chemicals. They have wide applications. They are used in sealant, greases, electrical insulators, waterproofing in fabrics. Waterproofing again, it is water repellent. Being biocompatible, they are also used in surgical and cosmetic plants, right? You must have heard about these silicon things, right? So basically, this is what they are talking about in cosmetic plants also. Now the Botox and all these treatments are way too famous in celebrities, right? So this is what they are doing to their bodies, right? Okay. Now, which is definitely not a good idea. Now we have silicates, right? Silicates. From silicons, just remember the repeating unit, okay? Just remember the repeating unit, right? You don't have to remember, mug up everything here. From silicates, right? A large number of silicates mineral exist in nature. Some of the examples are feldspar. Now, this is very important. Feldspar, zeolites, mica, and asbestos, right? From here, feldspar and zeolites are important. The basic structure, the name is important for you, right? That the large number of silicate exist. Some of the examples are feldspar, zeolites, mica, right? These examples are important. The basic structure unit of silicates is very, very, very important. This question also is being asked, right? In NEET, they can ask you this question. What is the repeating basic unit? Basic unit of silicons, basic unit of silicates. That is SiO4 negative. This you have to remember. Then in bonded to 4 oxygen atom in tetrahedral fashion. In silicates, either the discrete unit is present or a number of such units are joined together via corners by sharing 1, 2, 3. You don't have to remember the structure here. Don't remember it. Just remember the basic unit is SiO4 negative. Just remember this thing. Right? I'll tell you what else is important here. When silicate units are linked together, they form chain, right? Ring, sheet. Very important line, right? A very, very important line. Very important. Let me keep it here only. First important thing is feldspar, zeolites, mica, and this epstose. Right? Then you have what is the repeating unit here. Very, very important. Then you have this line. When silicate units link together, what they will form? They can form a chain. They can form a ring. They can form a sheet. They can form three-dimensional structures. Question can be asked. I have seen this question. That which of the following silicates exist? The option was also which of the following is silicates does not exist. One of the option was two-dimensional silicates. So the correct answer was two-dimensional silicates because two-dimensional silicates will not exist. Either chain or ring or sheet or three-dimensional silicates will exist. Right? Two-dimensional will not exist. Negative charge on silicate structure is basically neutralized by a positive charge metal ion. Simple. All the four corners are shared with other tetrahedral units. Three-dimensional network is formed. So basically this is what they are talking about, that this unit is going to repeat. They can form sheets, they can form rings, they can form chains, they can form three-dimensional structure. Right? Two important man-made silicates are glass and cement that we have used in our life. Right? Then we have zeolites, the last thing of this one. Zeolites, these are silicates only that are in your NCERT, so we will do that. Right? If aluminium atoms replace few, very, very important. If aluminium atoms replace few silicon atoms in three-dimensional network structure of silicon dioxide, right? If you have silicon dioxide, if some of the silicon is replaced by aluminium, that is called, overall structure is known as aluminosilicate, acquires a negative charge, right? Okay, that acquires a negative charge here, right? Because aluminium is 3 positive, silicon is 4 positive. That is why 1 positive is less here. That is why it will acquire a negative charge, right? Now it will need a positive ions to balance it. Examples are feldspar, zeolites. These are the 2 examples. Zeolites are widely used as catalyst in petrochemical industry for cracking hydrocarbon. I know you will be like, ma'am, what is all this? All this is, ma'am, cramming or what? No, I didn't have my dinner. Right, I'll have it. Right, after the class, I'll have it. Now, see all of these things, right? This is total cramming, right? Total cramming. I know that, right? This thing is not detailed in your syllabus. This itself is a very big topic, right? It's a different study, right? So you don't need to get into that much Googling it, ma'am. What are zeolites, ma'am? I need to understand. I want to do PhD in zeolites. You don't need to do that, right? They will ask, if they ask you something, they will ask from this paragraph only. They will not go beyond this paragraph, right? Okay, so you don't have to just Google everything. I want to go do PhD in this particular topic. You don't have to do that. If you want to spend your time, do PhD in something, then do PhD in electrochemistry, organic chemistry, reactions. That should be on your tips, right? So whatever I'm teaching you from this chapter, do that. Zeolites are widely used as catalyst in petrochemical industries for cracking of hydrocarbons and isomerism. In isomerism, isomerization, I have told you that zeolite. If you remember, I have told you that this thing was used. If you remember, in case of isomerism, when we were doing isomerization reactions, when we were converting one isomer to other, then I told you that zeolite will be used here. That is ZSM5, a type of zeolites used to convert alcohol directly to gasoline. Now, this is important for you. This is important. That from alcohol to gasoline, they will ask you which zeolite is used. Or they can ask you ZSM5 zeolite is used in which thing to convert alcohol directly to gasoline, right? Then hydrated zeolites are used as ion exchangers in softening of hard water. This is also important, that hydrated zeolites are used in softening of the hard water, right? These are 3-4 things for zeolites. One is, what is the definition? That we have few when silicon is replaced by aluminium, right? In your silicon dioxide silicates, right? That is called aluminosilicate. And the examples, very important, are feldspar and zeolites. And which zeolite is important for you? That ZSM5 is used to convert alcohol to gasoline, and some hydrated zeolites are used in ion exchanger for softening of hard water, right? Okay, guys. Now tell me, is that clear to everybody or not? Is that clear to everybody or not? Everybody in the chat box. Yes, everybody. Is that clear to you or not? Everyone in the chat box. Everyone in the chat box. Can I see some green hearts here? Can I see some green hearts on the chat box? Yes, Madhumati, Sneha, I have been standing here for just you guys, okay? I have been here just for you guys, right? Okay, so can I have some energy? Can I see something in the chat box? Because only for you I was standing here. I didn't have my dinner, right? So I was just standing here from 6 p.m. and this is almost 10 here, right? Why? Because I want you guys to not miss anything, right? I could have just told you that just do exceptions and trends, right? But I know still students will do these compounds and they will do it in a very wrong manner. They'll be like, I want to cram all the reactions. They don't know which thing is important for you, right? That is why from NCERT we are doing this, right? Next is group number 15 and 16 that we are going to do in the next lecture. That is already mentioned in your live section of this channel. Go and right now only hit that like button on that live lecture that I am going to take up after this, and also share this among your friends, okay? Don't be a lazy person, right? Share this lecture among your friends on your WhatsApp group, right? So that we can spread the knowledge that we are giving you. And also we are giving you one more thing here, right? That is totally free of cost we are giving you, right? Totally free of cost we are giving you that. Wait a minute. Yes, I can see some green hearts in the chat box. So how many of you? Welcome Pradeep, welcome Newton, Madhumati, Sneha, Wilson, thank you so much. Very good. I'm so happy that you guys are liking and actually sitting here for like 3-4 hours and studying, and for this I can guarantee you will get the reward of this thing, right? When you are sitting in your NEET exam, you will see everything ma'am has covered, right? Then you will feel that yes, I have the confidence, right? Even when you attempt the mock test, you will feel that yes, how much confidence you will feel because of these kind of lectures. Now guys, I want firstly to hit the like button and share this among your friends, right? So that we can have more students here, right? We can have more students who actually want to study in the comfort zone of their home, and they have no mentor and no guide who can guide them through this NEET journey, right? So you guys are already here. So I want you guys to click on this link where you have treasure box. How many of, let's do it along with me only. Now I want all the students who are present here, all the students present here, I want you guys, wait a minute, all the students present here, I want you guys to write it down in the chat box. Yes, everybody. I think, are you guys able to see each other's messages? Huh? Yes. Very good, very good. So right now, along with me, click on this treasure box, everybody. Here, if you talk about physics, if you talk about chemistry, you will get the YT link of NEET corresponding to that chapter. You will get the NEET previous class notes, right? For example, I click here, then I think I'll have to add my email ID here, which I don't have currently, right? So you just need to click here, then you just need to add your email ID or your number, then you will get to the notes here. Then previous year question test also you will give. Out of that, number marks will be given to you. Then if you want to do previous year question from the PDF, right? So chapter wise NEET previous year question PDF is given to you. CBSE NCERT solution is given to you, right? So you can just go through that for chemistry, physics, as well as bio, right? So just click on that and you will get to this portal and download everything here, right? Start practicing as much as possible. Now tell me how many of you have already clicked on this and taken advantage of the treasure box. Let me see how many of you. Sneha, Newton, because right now it is free, right? So take the advantage. If I tell that, okay, this is for this much amount, then you will say, ma'am, why can't you provide it for free, right? But right now it is free, but how much long it will be for free, I don't know, right? Okay. Yes, Pradeep has done it. Ithral has done it. Newton has done it, right? Okay. So that is your task for today. Go through this, pick up any chapter, do the previous year question test of that chapter, right? Okay. And I will ask you in the next class that which chapter previous year question test you did. Okay. So chalo, I'll give you one test. Okay. You can give the previous year question test for biomolecules. How many of you will give biomolecules previous year question test? Wait a minute. Previous year question, YT, previous year question test. Wait a minute. Let me see. Biomolecules. It is here. Right. This is a previous year question test. Okay. Click on this. You will get to the link here. Right. Okay. For biomolecules, how many of you are promising me that you will give biomolecules previous year question test tomorrow itself? And I will ask how many students have done that, right? Okay, I want you guys to make a habit of this. Let me see in the chat box how many of you will do that. I want to see that. Your teacher can stand here for so many hours. Can't you give one test for that, for your own self, right? So that you're able to realize that where actually you are doing the mistakes, right? I'll give the test, ma'am. Very good, Pradeep. How many other students? Newton is saying this, ma'am. I'll give the test. Biomolecules, very good. Ethereal, very good. It's not like ma'am won't be able to know that, right? I will ask you and I will be able to know that because you are going to add your name there now. So I will be able to know that if you have given the test or not, right? Okay. But you just have to give the test and tell me honestly whether what was the result of that test. And it's a very small test. It's just 10 questions you will have, maybe 10 to 15, right? So it will make your brain, right? You will have a practice that how to solve question when it is given in the MCQ form, right? Okay. Okay then, bye guys. Take care. See you all in the next class and where we are going to do group number 15 and group number 16. Okay, bye bye. See you all in the next class. Bye bye.